Every civilization leaves something behind. Most leave stories, artifacts, or ruins. A few leave mysteries that refuse to grow old. Scattered across the world are ancient structures so ambitious that even after centuries of study, experts still debate how they were designed, built, and why some were placed in locations that seem almost impossible to reach. Their builders vanished, their methods were never recorded, and many of their original purposes remain uncertain. Instead of becoming clearer with time, these monuments often become more puzzling as new discoveries reveal details no one expected to find. They remind us that history is not a completed story, but a puzzle with countless missing pieces still buried beneath the surface.
Located beneath the modern city of Alcalá de Henares, about 30 kilometers northeast of Madrid in central Spain, Complutum is one of the best preserved Roman cities on the Iberian Peninsula. At first glance, its streets, villas, and public buildings resemble many other Roman settlements, yet the engineering knowledge embedded beneath its stones continues to challenge archaeologists. Excavations reveal a city planned with remarkable geometric precision, supplied with clean water, protected by an advanced drainage network and decorated with wall paintings whose colours have survived nearly 2,000 years. While archaeologists understand what was built, many of the practical techniques that made it possible remain only partially explained. Complutum was known through historical references for centuries, but its true extent only became clear during systematic archaeological investigations that accelerated throughout the 20th century, particularly after urban expansion around Alcalá de Henares exposed Roman remains. Excavations eventually uncovered roughly 10 hectares of the ancient city, including the Forum, residential districts, workshops, streets, drainage channels, and the famous House of Hippolytus. Ceramic analysis, inscriptions, coins, and architectural evidence indicate that the city flourished mainly between the 1st and 4th centuries AD, although earlier occupation existed in nearby settlements before the Roman urban centre was established. Every excavation has revealed a city constructed according to an organised plan, rather than one that developed gradually through centuries of random expansion. That organisation immediately raises questions because the entire urban layout follows an orthogonal grid, with streets intersecting at almost perfect right angles. The principal roads divide the city into regular insulae, while public buildings occupy carefully selected central positions connected through a coordinated transportation network. Modern surveys show that many street alignments remain astonishingly consistent, despite centuries of erosion and later construction. Roman surveyors are known to have used instruments such as the groma, chorobates, and dioptra, yet no surviving documents explain exactly how survey teams maintain such accuracy across an expanding city without optical levels, satellite positioning, or modern measuring equipment. Even a small angular error repeated over several hundred meters would gradually distort the entire plan, but Complutum displays little evidence of cumulative surveying mistakes. Archaeologists can identify the final geometry preserved in stone, yet the exact workflow used to achieve this precision remains largely invisible because the temporary wooden markers, ropes, and measuring devices disappeared long ago. The deeper researchers investigate the city, the more impressive its hidden infrastructure becomes. Beneath many streets runs an extensive drainage system built from carefully fitted masonry channels that carried wastewater away using gravity alone. Hydraulic engineering depends almost entirely upon maintaining the correct gradient, because excessive slopes increase erosion, while insufficient slopes allow stagnant water and sediment accumulation. Modern civil engineers calculate these values using mathematical models and precision instruments, Yet Roman builders established stable drainage networks across an entire urban landscape nearly 2,000 years ago. Excavations demonstrate that many of these underground channels still preserve their original form, suggesting exceptionally careful construction. Archaeologists understand the physical principles involved, but cannot determine exactly how Roman engineers measured minute differences in elevation over long distances using only ancient surveying technology. The functioning network survives, while the techniques used to design it remain uncertain. The city's water supply presents an equally fascinating puzzle. Complutum possessed baths, fountains, private residences, and gardens that required reliable access to fresh water throughout the year. Archaeological investigations have identified lead pipes, ceramic conduits, cisterns, and distribution structures integrated into different parts of the city. Together, they demonstrate a sophisticated hydraulic system capable of supporting thousands of inhabitants. Yet the complete supply network has never been reconstructed with certainty. Some researchers propose connections to nearby springs through aqueducts, while others suggest a combination of groundwater extraction and local storage reservoirs. Neither explanation alone fully accounts for the flexibility implied by the surviving infrastructure. Unlike monumental aqueducts that remain visible above ground elsewhere in the Roman Empire, much of Complutum's hydraulic system vanished beneath later occupation, leaving archaeologists with isolated fragments rather than a complete engineering blueprint. As excavation expanded into elite residences, another technological mystery emerged from surfaces rather than foundations. The wall paintings preserved inside several Roman houses remain among the most remarkable discoveries at Complutum, because many still retain vivid reds, yellows, blacks, and traces of green, despite exposure to nearly 20 centuries of chemical weathering. Scientific analyses identify pigments including red hematite, yellow ochre, carbon-based black and copper-derived minerals, materials commonly used throughout the Roman world. Their composition is no longer surprising. Their extraordinary preservation is. Roman artists applied these pigments onto fresh lime plaster using the fresco technique, allowing calcium carbonate crystals formed during curing to lock the colours permanently into the wall itself. Laboratory studies confirm this mineral bonding process, yet they do not fully explain why certain murals at Complutum survived with exceptional stability, while others in comparable environments deteriorated far more rapidly. Microscopic examination reveals multiple plaster layers containing carefully selected aggregates, lime and fine mineral particles, but the precise proportions, curing conditions, and construction sequence that produce such durable surfaces remain impossible to reconstruct with complete confidence. Environmental factors certainly contributed, yet preservation alone cannot explain the remarkable consistency observed across several decorated rooms. The paintings therefore represent not merely artistic achievements, but evidence of sophisticated materials engineering whose practical recipes disappeared with the craftsmen who mastered them. That same attention to precision appears again in the famous mosaics of the House of Hippolytus, where thousands of tiny tesserae formed geometric patterns and marine scenes with astonishing regularity. Individual stone cubes differ only slightly in size. Curved lines remain smooth across large compositions, and spacing rarely deviates enough to disturb the overall design. Producing such consistency required careful planning long before the first tessera was placed. Archaeologists assume preliminary guidelines were drawn onto prepared mortar surfaces, yet almost no physical evidence survives because those temporary marks disappeared beneath the finished mosaic. The final artwork demonstrates exceptional geometric control, but the practical layout methods remain largely theoretical. The durability of complutum extends beyond decoration into the buildings themselves. Many surviving walls remain remarkably stable despite almost 2 millennia of seasonal temperature changes, groundwater movement, and occasional seismic activity affecting central Spain. Excavations indicate that Roman builders adapted foundations to local geological conditions, using compacted stone, lime mortar, and carefully selected construction materials, but the exact sequence of preparation varies between structures. Some walls continue standing with minimal displacement, while neighbouring sections collapsed centuries ago, suggesting that builders modified construction techniques according to soil conditions rather than following a single standardised method. Modern archaeology can observe these results directly, but cannot always identify the engineering decisions responsible for their long-term performance, because the earliest construction phases often lie buried beneath later rebuilding. Research keeps improving our understanding of complutum through tools like stratigraphy, ceramics, inscriptions, material analysis, and GIS. These help date the city, trace trade links, and show how it worked within the Roman world, but many questions remain. The site clearly shows what Roman engineers achieved, yet the practical know-how behind it is still unclear. Complutum is more than ruins, it's a rare glimpse of lost engineering skills that were never properly written down. The ruins of Bilbilis rise across steep limestone hills near modern Calatayud in Zaragoza province, northeastern Spain, where slopes exceeding 30 degrees create one of the most improbable Roman cities ever constructed. While travellers often remember its theatre or its connection to the poet Martial, archaeologists increasingly regard Bilbilis as an engineering achievement, whose construction methods remain only partially understood despite more than a century of excavation. The site first attracted scholarly attention during the 19th century when scattered inscriptions, architectural fragments, and references in classical texts suggested the location of the Roman municipium of Augusta Bilbilis. Systematic archaeological excavations beginning in the early 20th century, followed by extensive surveys using photogrammetry, topographic mapping, and architectural analysis, gradually revealed a city occupying more than 20 hectares. Instead of standing on a level plateau like many Roman colonial foundations, Bilbilis unfolded across a succession of narrow terraces, carved into a mountainside, immediately raising a question that modern archaeology still cannot answer completely. How did Roman engineers transform such unstable terrain into an urban landscape capable of supporting thousands of people for centuries? Everything begins with the mountain itself. Geological studies identify the hill as composed primarily of Jurassic limestone, overlying layers that naturally fracture and weather under seasonal rainfall. On slopes approaching or exceeding 30 degrees, gravity continuously encourages soil movement, increasing the risk of landslides and differential settlement. Modern engineers normally solve such problems through reinforced concrete retaining structures, deep foundations, computer-based slope stability models, and continuous geotechnical monitoring. Roman builders possessed none of these technologies, yet they succeeded in constructing temples, baths, houses, warehouses, administrative buildings, and one of the largest theatres in inland Hispania upon the same unstable terrain. Excavations reveal an immense system of artificial terraces rather than a simple adaptation of natural landforms. Entire sections of the mountain were cut away while other areas were built outward, using enormous retaining walls that redistributed weight across the slope. The remarkable survival of this terraces after nearly 2,000 years suggests an understanding of load transfer and hillside stabilization, far more sophisticated than surviving Roman construction manuals describe. That observation naturally leads to another mystery surrounding the retaining walls themselves. Many remain standing despite centuries of erosion, earthquakes, seasonal temperature variation, and repeated human occupation. Their stability cannot be explained merely by the strength of Roman concrete, because much of the supporting system depends upon carefully positioned limestone blocks, working together with fills of crushed stone and compacted material behind the walls. Archaeologists have identified the visible structures, but the complete construction sequence remains uncertain because temporary scaffolding, timber supports, drainage channels, and measuring equipment disappeared long ago. Without those missing elements, researchers can reconstruct only the finished result, not the practical engineering decisions that made the project possible. As the city expanded across multiple elevation levels, another challenge emerged. Every additional building increased pressure upon the terraces below. Excavation beneath several structures has revealed layered foundation systems consisting of large stones, smaller aggregate, and compacted fills designed to distribute weight gradually into the hillside rather than concentrating stress at individual points. Similar principles remain fundamental in modern geotechnical engineering, yet no surviving Roman document explains how builders determined the thickness, composition, or sequence of these foundation layers. Their decisions appear remarkably consistent throughout Bilbilis, implying standardized technical knowledge that has largely vanished from the historical record. The famous theatre demonstrates this mastery even more clearly. Archaeological measurements indicate that it could accommodate approximately 4,500 spectators, making it one of the largest public structures in the region. Rather than constructing the entire cavea above ground, Roman engineers excavated portions directly into the mountain while supporting other sections with artificial substructures where natural rock was insufficient. This hybrid solution minimized material requirements while exploiting the mechanical strength of the hillside itself. Yet the transition between excavated bedrock and constructed masonry demanded exceptional precision because uneven settlement would have produced cracking throughout the seating tiers. The surviving remains indicate that such structural failure never became catastrophic, although the methods used to achieve that stability remain largely speculative. Once the terraces existed, supplying water became an equally difficult problem. Bilbilis occupied elevated ground chosen for defense and visibility rather than convenience. Water therefore had to be collected, transported, and distributed uphill across changing elevations. Archaeologists have uncovered cisterns, lead pipes, stone channels, and distribution basins, demonstrating an advanced hydraulic network integrated into the urban plan. Roman hydraulic engineering is well documented elsewhere, yet Bilbilis presents unresolved questions because significant portions of its aqueduct system have disappeared. Researchers still debate the exact capture points, the complete route of water delivery, and the hydraulic pressures maintained throughout the network. Without those missing sections, the city's full water management strategy cannot yet be reconstructed with confidence. The movement of water also affected another hidden engineering problem. Rain falling on steep mountainsides rapidly accelerates erosion, threatening foundations and retaining walls alike. Excavations of exposed underground drainage channels directing runoff away from critical structures before destructive pressure could accumulate behind terrace walls. Several passages continue to function after almost 2 millennia, indicating remarkably accurate calculations of slope, gradient, and discharge capacity. Nevertheless, large portions of the drainage system remain buried beneath unexcavated sectors of the city, leaving archaeologists unable to map the complete network or determine whether it evolved through multiple construction phases. These engineering achievements become even more remarkable when considered alongside the precision of the city's urban planning. Roman surveyors relied primarily upon instruments such as the groma for establishing right angles, and the chorobates for measuring level surfaces. Those tools worked effectively on open plains, yet Bilbilis offered neither level ground nor unobstructed sightlines. Despite these limitations, modern architectural surveys reveal carefully aligned streets, coordinated public buildings, and modular planning adapted to highly irregular topography. Rather than forcing an artificial grid upon the mountain, planners subtly modified Roman urban principles to fit the landscape while preserving functional relationships between civic spaces. The accuracy visible today raises an obvious question. How did surveyors maintain consistent geometric control across steep, fragmented terrain without modern optical instruments or digital mapping? Construction logistics present one final puzzle. Thousands of tons of limestone had to be quarried, transported uphill, positioned with remarkable precision, and incorporated into terraces long before powered machinery existed. No permanent construction ramps survive. No lifting equipment has been discovered, and no written account describes the methods employed specifically at Bilbilis. Archaeologists generally propose combinations of wooden sledges, rollers, cranes driven by tread wheels, ropes, and coordinated human labour, because comparable technologies appear elsewhere in the Roman world. Even so, the archaeological evidence at Bilbilis itself remains indirect. The city preserves the completed engineering, but almost none of the temporary infrastructure that allowed it to exist. Located beneath the modern cities of Izumi and Izumiotsu in Osaka Prefecture, Japan, Ikegami-Sone appears at first to be an ordinary archaeological site, yet beneath the soil lies evidence of engineering so sophisticated that archaeologists still cannot fully explain how it was achieved nearly 2,000 years ago. The site was identified in the early 20th century, but its true importance emerged after large-scale excavations beginning in the 1970s uncovered one of the largest Yayoi settlements ever discovered. Covering more than 60 hectares and occupied from approximately the 1st century BCE to the 3rd century CE, Ikegami-Sone revealed hundreds of buildings, defensive ditches, workshops, storage facilities, and one extraordinary wooden structure unlike anything previously known from the Yayoi period. Among all the discoveries, nothing has generated more debate than the enormous pillar foundations standing near the centre of the settlement. Archaeologists uncovered two massive post holes, measuring nearly 2 meters in diameter, each originally supporting a gigantic wooden column cut from camphor trees. Analysis of the post holes and preserved timber indicates that each trunk measured roughly 70 to 90 centimeters across, while reconstruction suggests the columns may have risen more than 10 meters above the ground and perhaps even approached 15 meters. Such dimensions immediately raise a difficult engineering question, because no written record survives to explain what kind of building required supports of this scale. Some researchers interpret the structure as a ceremonial tower visible across the surrounding plain. Others suggest an elevated granary, a monumental gateway, or the foundation of a large administrative building. Yet none of these theories fully explains why only 2 enormous pillars were necessary. Without surviving upper architecture, the purpose of the structure remains one of the greatest unresolved mysteries of prehistoric Japan. That uncertainty becomes even greater when considering the practical challenge of construction. A mature camphor tree with a trunk approaching 1 meter in diameter can weigh many tons before processing, and even after trimming, transporting such timber without iron machinery, wheeled transport capable of carrying extremely heavy loads, or draft animals on a large scale would have required remarkable organization. Archaeologists have proposed the use of wooden rollers, ropes woven from plant fibers, earthen ramps, and coordinated human labor, but no direct archaeological evidence has revealed the actual construction method. Unlike Egyptian pyramids or Roman monuments, no construction tools, transport tracks, or unfinished lifting systems have been preserved. The builders clearly possessed techniques capable of solving these logistical problems, yet those techniques disappeared without leaving written instructions, forcing modern researchers to reconstruct the process largely through experimental archaeology. Even more remarkable is the deliberate choice of camphor wood itself. This decision appears far too sophisticated to have been accidental. Camphor trees produce natural aromatic compounds that resist insects and fungal decay, making the timber exceptionally durable in Japan's humid climate. The wood also possesses considerable structural strength while remaining relatively resistant to splitting during long-term use. Selecting such material implies that Yayoi builders possessed accumulated empirical knowledge about the mechanical behavior of different tree species, understanding not only which woods could support enormous vertical loads, but also which could survive decades or even centuries under constant exposure to moisture. What remains unexplained is how this knowledge developed. No surviving documents describe forestry management, timber classification, or construction manuals from the Yayoi period because writing had not yet become established in Japan. The expertise must therefore have been transmitted through generations of craftsmen entirely by observation and practice. Modern engineers can explain why camphor performs well as a structural material, but they cannot determine how prehistoric builders acquired such advanced practical knowledge without formal scientific methods. The enormous pillars at Ikegami-sone therefore represent not only an architectural mystery, but also a lost tradition of material engineering whose origins remain invisible. This sophisticated understanding of materials appears throughout the settlement itself. Excavations reveal that Ikegami-sone was not an irregular village expanding randomly over time, but a carefully organized community with residential districts, workshops, storage buildings, ritual spaces and open areas arranged according to an overall plan. Several rows of buildings follow consistent orientations, suggesting deliberate surveying before construction began. Creating such an organized settlement across more than 60 hectares would have required accurate measurement, planning and coordination among large numbers of workers. Yet archaeologists have recovered no standardized measuring rods, surveying instruments, or construction drawings capable of explaining how this precision was achieved. The regularity suggests that builders relied upon established systems of proportion and alignment that have completely vanished from the archaeological record. The location itself introduces another engineering puzzle. Osaka's lowlands are characterized by soft alluvial sediments deposited by rivers over thousands of years, conditions that normally complicate the construction of heavy timber structures. Massive wooden columns placed directly into unstable ground would gradually lean or sink as the soil compressed beneath them. Excavation, however, indicates that the giant post holes were prepared with exceptional care before the columns were installed. Their depth, shape, and surrounding soil suggest that builders understood the importance of creating stable foundations capable of distributing enormous loads. Whether they intentionally compacted the ground, added gravel, improved drainage, or employed another technique remains uncertain because organic evidence rarely survives after nearly 2 millennia. Nevertheless, the stability implied by these foundations demonstrates practical geotechnical knowledge far beyond what is often assumed for prehistoric farming communities. Water management throughout Ikegami-sone presents another example of unexpected technical ability. The settlement occupied a region vulnerable to seasonal rainfall, yet excavations uncovered networks of ditches, drainage channels, and carefully elevated construction platforms that reduced flooding around important buildings. Rather than relying upon stone-lined canals or hydraulic cement, the inhabitants shaped the landscape itself, controlling runoff through subtle changes in elevation and interconnected earthworks. Such systems required long-term observation of rainfall patterns, groundwater movement, and seasonal flooding. Their success is demonstrated by the settlement's continuous occupation for several centuries despite challenging environmental conditions. Exactly how these drainage systems were designed, without written calculations or permanent engineering institutions, remains unknown. The settlement also functioned as a major production centre rather than a simple farming village. Archaeologists discovered evidence of woodworking, stone tool manufacture, pottery production, weaving, and bronze casting, indicating a highly specialized economy supported by skilled craftspeople. Such industrial diversity implies organized labor, reliable food storage, and administrative coordination capable of sustaining specialists who were not directly engaged in agriculture. Yet no palace, archive, or written administrative record has ever been found. The existence of complex economic management is therefore inferred entirely from physical evidence, leaving historians unable to identify the individuals or institutions responsible for directing such an advanced community. Perched atop a colossal limestone mesa in Burgos province, northern Spain, Peñaramaya rises about 1,377 meters above sea level, where sheer cliffs protect a plateau that has challenged invaders for more than 2,000 years. Long before modern surveying, cranes, or engineering software, ancient builders transformed this isolated summit into one of Iberia's most formidable strongholds, leaving behind construction methods that archaeology still cannot fully explain. The site attracted scholarly attention during the 19th century, while systematic archaeological excavations carried out throughout the 20th century uncovered successive layers of occupation dating from the Late Bronze Age, flourishing during the Iron Age under the Cantabri, continuing through Roman control, the Visigothic kingdom, and the early medieval period. Radiocarbon dating, ceramic, typology, coins, and architectural remains reveal an almost continuous sequence of settlement extending across more than 2 millennia. Yet these discoveries answered only part of the story, while exposing even deeper engineering mysteries. What immediately separates Peñaramaya from countless other hill forts is not simply its elevation, but the astonishing way its builders turned the mountain itself into their greatest defensive weapon. The limestone plateau is surrounded on most sides by vertical escarpments rising between roughly 100 and 200 meters, creating natural walls that no army could easily scale. Instead of attempting to enclose the entire settlement with massive artificial fortifications, its engineers carefully studied every contour of the landscape and reinforced only the few vulnerable approaches. Modern topographic analysis indicates that nearly 3/4 of the perimeter required little or no constructed wall, because the cliffs already formed an almost impenetrable barrier. This remarkable economy of labor demonstrates a sophisticated understanding of terrain analysis that resembles principles still taught in military engineering today. Without aerial photography, contour maps, or precision instruments, they somehow identified every weak point where attackers could realistically approach, while allowing the mountain itself to perform most of the defensive work. Archaeologists can observe the final result in stone, yet no surviving evidence explains how such an accurate assessment of three-dimensional terrain was originally achieved. This exceptional adaptation to the landscape naturally raises another unresolved question concerning construction itself. Although the summit appears inaccessible from below, excavations have uncovered extensive stone walls, residential buildings, storage facilities, defensive gateways, and water installations, all requiring thousands of tons of limestone to be transported uphill. No preserved ramps, lifting devices, or permanent transport roads have been identified, experimental archaeology demonstrates that prehistoric communities could move multi-ton stones using wooden sledges, rollers, ropes, and coordinated human labor. But direct evidence for these systems has disappeared from Peña Amaya. Temporary timber structures would have decayed long ago, leaving researchers to reconstruct possible methods only through comparison with similar Iron Age settlements across the Iberian Peninsula. The finished architecture survives, while the engineering process that created it remains almost completely invisible. The builders also faced another obstacle hidden beneath their feet. Unlike many ancient cities established on relatively level ground, the summit of Peña Amaya consists of uneven limestone surfaces broken by natural ridges, fissures, and irregular slopes. Archaeological surveys reveal that large sections were reshaped into stable terraces capable of supporting houses, workshops, and defensive structures. Achieving these flat construction platforms required cutting bedrock, filling depressions and stabilizing retaining edges with carefully positioned masonry. Surprisingly, little waste stone has been identified around the settlement, suggesting that excavated rock may have been immediately recycled into walls and foundations with extraordinary efficiency. Even today, determining exactly how much of the visible landscape is natural and how much was modified by human labor remains an active subject of archaeological investigation. As researchers continued examining the plateau, attention shifted toward an equally important challenge that every permanent mountain settlement must solve. The summit contains no substantial natural spring capable of supplying a large population throughout the year. Nevertheless, excavations identified cisterns, rock-cut basins, and drainage channels designed to capture seasonal rainfall. Northern Spain receives an average annual precipitation approaching 700 millimeters in many surrounding regions, making rainwater harvesting practical if storage systems were carefully engineered. The unanswered question concerns their long-term performance. Archaeologists still debate the original storage capacity, waterproofing techniques, and maintenance procedures because much of the hydraulic infrastructure has deteriorated over centuries of erosion. Some reservoirs continued retaining water long after abandonment, implying that their builders possessed a sophisticated understanding of impermeable clay layers or mineral-based sealing materials whose exact composition has yet to be confirmed through scientific analysis. The entrances to Peña Amaya reveal another level of strategic planning. Rather than providing broad access to the plateau, surviving gateways force movement through narrow passages where advancing troops would have been compressed into small groups before reaching the interior. This bottleneck design dramatically reduced the numerical advantage of attacking forces while exposing them to defenders positioned above. Military historians recognize similar concepts in later fortified cities throughout Europe, yet Peña Amaya demonstrates that these tactical principles had already been mastered centuries before medieval castle design reached its peak. Whether this knowledge developed independently among the Cantabri or gradually evolved through generations of practical warfare remains impossible to determine, because no written military manuals from the settlement have survived. Equally impressive is the endurance of the dry stone masonry itself. Many surviving wall segments have remained standing despite repeated freeze-thaw cycles, earthquakes of minor intensity, and more than 2,000 years of weathering. Unlike structures bonded with mortar, dry stone construction distributes stress through precisely selected blocks, whose weight and geometry allow slight movement without catastrophic collapse. Modern engineering studies have shown that well-built dry stone walls can absorb ground deformation more effectively than rigid masonry, but they also require remarkable craftsmanship during construction. At Peña Amaya, individual stones were shaped only enough to maximize contact while preserving structural flexibility. Yet archaeologists still cannot reconstruct the exact selection rules or construction sequence followed by the original masons. The organisation of the settlement suggests that these achievements were not isolated acts of practical building, but components of deliberate urban planning. Excavated remains indicate separate residential sectors, storage areas, defensive installations and circulation routes, arranged according to the irregular terrain rather than imposed upon it. Instead of forcing geometric order onto the mountain, the builders adapted every structure to existing rock formations, minimizing excavation while maximizing usable space. This planning philosophy differs significantly from the orthogonal layouts later introduced by Roman colonial towns, illustrating that sophisticated urban organization could emerge through intimate knowledge of local geology rather than standardized architectural grids. Perhaps the strongest evidence for the effectiveness of these engineering decisions lies in the site's extraordinary longevity. Following the Roman conquest of the Cantabria during the late 1st century BC, Peña Amaya continued to be occupied instead of abandoned. Later Visigothic rulers recognized its strategic importance, and during the early medieval period, it again became a significant political center before eventually declining. Across each successive occupation, new inhabitants repeatedly reused earlier defensive works instead of replacing them entirely. Such continuity suggests that the original Iron Age engineering was already so well adapted to the mountain that later civilizations found little reason to redesign its essential structure. The ruins of Itokazu Castle stand among the limestone hills of Nanjo on Okinawa Island, Japan, appearing modest compared with the famous castles of East Asia. Yet beneath its weathered stone walls lies one of the least understood engineering achievements of the Ryukyu Kingdom. Built between the 13th and 14th centuries, this fortress still raises questions that modern archaeology cannot fully answer, especially how its builders transformed one of the most unstable limestone landscapes into a defensive structure that has survived for more than 6 centuries. The site became known to modern archaeology through surveys of Okinawa's medieval asterisk, Gusuku asterisk, castles during the 20th century, and systematic excavations later confirmed that Itokazu belonged to the network of fortified settlements that protected the southern Ryukyu Kingdom before its political unification in the early 15th century. Archaeologists uncovered sections of curtain walls, gateways, terraces, ceramics imported from China and Southeast Asia, and local Ryukyuan pottery, allowing the castle to be dated to the Gusuku period. Despite these discoveries, excavation has revealed remarkably little about the engineering methods behind the fortress itself, leaving the stonework to speak almost entirely for its forgotten builders. The greatest mystery begins with the landscape. Unlike castles constructed on broad hills or mountain ridges, Itokazu occupies an elevated platform formed from Ryukyu limestone, a coral-derived rock deposited during the Pleistocene and uplifted by tectonic activity over hundreds of thousands of years. Geological surveys show that this limestone is heavily affected by karst erosion, producing sinkholes, sharp ridges, underground cavities, fractures, and irregular slopes. Modern engineers generally avoid placing heavy masonry directly on such terrain, because hidden voids and uneven load distribution can cause gradual settlement or sudden collapse. Yet the Ryukyu builders selected precisely this difficult landscape and somehow converted it into a remarkably stable foundation without leaving evidence of large-scale ground leveling. Instead of forcing the mountain to match a design, they appear to have designed every section of the castle around the mountain itself. Many surviving walls follow natural contours with almost mathematical precision, suggesting that the builders possessed an intimate understanding of the rock beneath their feet long before geological science existed. Exactly how they evaluated which areas could safely support several tons of stone remains completely unknown. That uncertainty becomes even more remarkable when examining the walls themselves. Much of Itokazu Castle was constructed using a technique known as asterisk nozurazumi asterisk, in which irregular natural stones are stacked without mortar. Unlike later Japanese castles that relied on carefully shaped blocks, these builders worked with stones of widely different dimensions while still producing walls capable of resisting gravity, heavy rainfall, earthquakes, and repeated typhoons. Engineers studying similar dry stone structures have demonstrated that stability depends not only on the weight of individual blocks, but also on the distribution of contact surfaces and internal friction throughout the entire wall. Every misplaced stone changes the forces acting on dozens of surrounding stones. At Itokazu, the walls appear to achieve this balance despite the absence of standardized block sizes. Some researchers believe the masons intentionally aligned each stone along natural fracture planes within the limestone, reducing stress concentrations and improving long-term stability. But no historical record survives to confirm whether this sophisticated practice was actually employed or whether it resulted from generations of accumulated practical experience. As the structure extends across the ridge, another pattern begins to emerge. Rather than imposing symmetrical geometry, nearly every wall bends gently with the landscape. The castle's layout appears irregular when viewed from above, yet field surveys reveal that entrances, terraces, defensive corners, and retaining walls consistently follow changes in elevation instead of ignoring them. This suggests that the builders prioritize structural efficiency over visual order. Modern topographic engineering follows the same principle because adapting construction to existing contours minimizes excavation while reducing instability caused by artificial cuts into the slope. It is remarkable that medieval builders working without modern surveying instruments produced a fortress displaying many of these same characteristics. Whether they relied on wooden leveling tools, observation, accumulated craftsmanship, or methods now entirely lost remains one of the unanswered questions surrounding the site. The defensive design also reflects an unexpectedly advanced understanding of terrain. Unlike many medieval fortifications that relied on massive moats or towering keeps, Itokazu transformed the surrounding landscape into the primary weapon. Steep limestone escarpments restricted movement, narrow passages forced attackers into confined spaces, and successive changes in direction prevented large formations from advancing efficiently. Archaeological mapping indicates that several gateways required approaching forces to slow down while exposing themselves from multiple directions simultaneously. This arrangement resembles defensive concepts found in much larger castles despite being achieved largely through natural topography rather than monumental construction. Whether these passages were intentionally calculated through repeated military experience or simply evolved from adapting to the existing rock remains impossible to determine. The mountain itself conceals another mystery beneath the visible walls. Karst landscapes naturally develop underground caves as slightly acidic rainwater dissolves limestone over thousands of years. Beneath and around Itokazu lies a network of such cavities, some still only partially explored. Several entrances appear to have been modified by human activity, raising the possibility that natural caves became integrated into the castle's defensive system. Archaeologists have proposed that these underground spaces may have served as shelters, storage chambers, or concealed movement routes during periods of conflict, yet definitive evidence has never been recovered. The incomplete exploration of the cave system means the full relationship between the fortress above and the landscape below remains uncertain. Water management presents another engineering puzzle. Limestone rapidly absorbs rainfall through fractures, making permanent surface water scarce on elevated karst terrain. Any fortress expecting to withstand a siege required a dependable water supply, yet Itokazu sits on ground where rain disappears underground almost immediately. Small springs and water sources exist within the broader limestone region, but researchers continue debating how the castle maintained sufficient supplies during prolonged occupation. Some believe rainwater was directed toward naturally sealed depressions, where it could be collected before infiltrating the rock, while others suggest access to groundwater through nearby karst springs. Without surviving hydraulic structures or written documentation, the precise solution remains unknown, although the continued occupation of the fortress strongly suggests that its inhabitants had developed an effective system adapted specifically to this challenging geology. Environmental resilience offers another clue to the builders' remarkable understanding of their surroundings. Okinawa experiences one of the most destructive typhoon climates in East Asia, with annual storms frequently producing winds exceeding 200 kilometers per hour and intense seasonal rainfall. Such conditions accelerate erosion, destabilize slopes, and damage poorly constructed masonry. Even so, significant portions of Itokazu's stone walls remain standing after more than 600 years. Modern structural studies of dry stone walls show that slight flexibility can actually improve resistance to ground movement, because individual stones absorb and redistribute forces rather than transferring them through rigid mortar joints. Whether the Ryukyu builders intentionally exploited this mechanical advantage cannot be proven, but the fortress demonstrates that their construction methods were exceptionally well suited to Okinawa's severe environmental conditions. Kill Stone Circle stands above Bantry Bay in County Cork, Ireland, as a Bronze Age monument so precisely positioned that even today archaeologists continue to debate whether its builders were creating a ceremonial sanctuary, an astronomical observatory, or both. Built roughly between 2,500 and 2,000 years before Christ, this modest ring of stones occupies one of the most commanding viewpoints in southwest Ireland, where every direction appears deliberately chosen rather than accidental. Unlike Stonehenge, Kill attracts relatively little attention, yet its location, orientation and engineering preserve questions that modern science still cannot fully answer. The monument first entered modern archaeological records during 19th century surveys of Ireland's prehistoric monuments, although local communities had known of its existence for centuries. Systematic documentation by later researchers revealed that the site consists of a 5-stone circle approximately 8 meters in diameter, accompanied by a distinctive radial cairn formed by 2 large boulders balanced upon upright supporting stones. Excavations have remained limited because preserving the fragile monument takes priority, leaving many aspects of its construction hidden beneath undisturbed ground. As more accurate topographic mapping, satellite positioning and archaeoastronomical analysis became available during the late 20th and early 21st centuries, researchers realized that the true mystery of Kill was not the size of the monument, but the astonishing precision of where it had been built. That realization immediately raises a difficult question because southwestern Ireland contains countless hills, ridges and rocky outcrops suitable for constructing a stone circle. Yet the builders selected one specific terrace overlooking Bantry Bay, with an almost uninterrupted horizon stretching across mountain peaks and distant valleys. Statistical studies of Irish Bronze Age monuments demonstrate that many ceremonial sites occupy elevated terrain, but Kill belongs to a much smaller group where visibility appears exceptionally optimized. From the circle, observers can follow the movement of the sun along the eastern skyline, while maintaining a panoramic view extending toward the Caha Mountains. Modern geographic information systems show that only a limited number of nearby locations provide equally unobstructed astronomical sightlines, suggesting the choice of this hill required careful surveying rather than chance. The challenge is understanding how people without maps, compasses, optical instruments, or written mathematics identified the exact point capable of producing these alignments. The precision becomes even more remarkable when researchers examine the orientation of individual stones instead of the monument as a whole. Several archaeological surveys indicate that the entrance axis and the nearby radial cairn correspond closely with the direction of sunrise around the winter solstice, while other possible sightlines have been proposed for significant lunar events. Although debate continues regarding every measured alignment, the probability that multiple prominent landscape features accidentally coincide with important celestial positions continues to attract scientific attention. The Earth rotates with extraordinary regularity, allowing sunrise positions to shift predictably throughout the year by several tens of degrees along the horizon depending on latitude. Determining these extremes without modern instruments would require repeated observations over many years, careful memory and an organized method for preserving astronomical knowledge across generations. No written records survive from Bronze Age Ireland, making the intellectual process behind such measurements one of Caolcill's greatest unsolved technological mysteries. This problem becomes even more complicated when the movement of the moon is considered. Unlike the sun, whose annual cycle repeats consistently, the moon follows a much more complex pattern influenced by an approximately 18.6-year nodal cycle known as the major lunar standstill. During these rare periods, moonrise and moonset reach their most extreme positions along the horizon before gradually reversing over nearly 2 decades. Several prehistoric monuments across Britain and Ireland have been proposed as possible lunar observatories because their alignments appear consistent with these events. Some researchers have suggested that Caolcill may also preserve elements of this tradition, although the evidence remains actively debated. If such observations were intentional, the builders would have needed to monitor the sky continuously across almost an entire generation before confirming the cycle. No surviving artifact explains how this knowledge was recorded. Whether through oral tradition, ritual specialists, or repeated communal observations, leaving archaeologists with a remarkable scientific achievement, but no surviving explanation of the methods behind it. As the astronomical questions deepen, the engineering challenges become equally difficult to explain. The standing stones themselves reach nearly 2 meters in height, with individual weights estimated at several tons depending on density and shape. Geological analysis indicates that the stones are local sandstone and related materials available within the surrounding region, rather than transported from distant counties, yet moving multi-ton blocks across uneven slopes without wheeled vehicles remains a demanding task. Experimental archaeology has demonstrated that wooden sledges, timber rollers, ropes made from plant fibers and coordinated human labor can move stones weighing several tons under controlled conditions. Nevertheless, no direct archaeological evidence has been discovered at Caolcill preserving transport tracks, construction ramps, or specialized lifting equipment. Everything proposed today remains a reconstruction based on engineering principles rather than excavated proof. Even after transport, raising each stone introduces another technological puzzle. Modern structural engineering shows that a standing monolith remains stable only when its center of gravity falls safely within its buried foundation and surrounding soil can resist long-term rotational movement caused by wind, rainfall, and seasonal ground expansion. Southwest Ireland experiences heavy Atlantic rainfall, frequent storms, and centuries of soil erosion, conditions that should gradually destabilize poorly constructed megaliths. Yet Kerl has remained standing for nearly 4,000 years with surprisingly little displacement. Archaeologists suspect that carefully prepared foundation pits and precisely selected stone geometries contributed to this stability. But excavation beneath the monument is intentionally restricted to avoid damaging an irreplaceable archaeological site. As a result, the builder's exact engineering techniques remain hidden below the surface. The radial cairn introduces another mystery rarely found elsewhere. Two massive boulders rest upon upright supporting stones, creating an architectural form unlike the simple circles associated with many other Irish monuments. At first glance, the arrangement appears ceremonial, yet its placement relative to the circle and surrounding landscape suggests something more deliberate than symbolic decoration. Some archaeologists argue that the structure functioned as a fixed observation marker, framing particular celestial events on the horizon, while others interpret it as part of ritual architecture, emphasizing sacred directions within the landscape. Because no inscriptions, carvings, or associated artifacts identify its purpose, every interpretation must rely upon spatial analysis rather than direct historical evidence. The remarkable accuracy of its placement nevertheless implies that whoever designed the monument possessed a sophisticated understanding of geometry in open landscapes, even if that knowledge was never expressed through written mathematics. Chao Samartin stands in the mountains of western Asturias in northern Spain, rising above the Navia River valley like an ordinary hill. Yet beneath its grassy slopes lies one of the most technologically sophisticated Iron Age settlements ever discovered on the Iberian Peninsula, a place where advanced engineering, large-scale metallurgy, and carefully planned defences appeared centuries before Rome established control over the region. Its significance only became clear in the 1960s when accidental discoveries drew archaeological attention to the hill. But systematic excavations beginning in the 1990s transformed understanding of the site. Researchers uncovered successive occupation layers extending from approximately the 8th century BC through the Roman period and into the early Middle Ages. Because later construction never completely erased the earlier settlement, archaeologists were able to reconstruct more than 1,000 years of continuous technological development. Radiocarbon dating, ceramic typology, and imported Roman materials together established an unusually reliable chronological sequence, making Chao Samartin one of the best documented Castro settlements in northwestern Spain. What immediately distinguishes the settlement is not simply its age, but the remarkable way its builders reshaped an uneven mountain summit into a stable urban platform. The natural hill consists of fractured slate and steep slopes that should have been highly vulnerable to erosion, yet its inhabitants created extensive artificial terraces capable of supporting houses, workshops, and defensive structures over many centuries. These terraces were retained by carefully constructed stone walls that still remained standing after more than 2,000 years despite repeated exposure to heavy Atlantic rainfall. Modern geotechnical engineering explains that retaining walls survive only when builders successfully balance earth pressure, drainage capacity, and structural weight. But no surveying instruments, measurement standards, or construction manuals have survived to explain how Iron Age engineers achieved such long-term stability using only local stone and manual labour. That sophisticated understanding continues inside the defensive system. Rather than relying upon a single enclosure, Chao Samartin expanded through multiple construction phases that added new walls while preserving earlier fortifications. The resulting concentric layout forced anyone approaching the settlement to negotiate narrow passages, abrupt turns, and elevated gateways before reaching the interior. Archaeologists have noted that these controlled access routes dramatically reduce the effectiveness of a direct assault while exposing attackers to defenders positioned above them. Similar defensive principles later became common in Roman military architecture, yet Chaucer-Martin demonstrates that comparable concepts already existed among indigenous communities centuries earlier. Whether these solutions emerged independently or developed through long-distance cultural exchange remains impossible to determine, because no written records describe the design process. As excavation moved deeper into the settlement, however, the greatest surprise appeared not inside the walls, but within the industrial quarter. Archaeologists uncovered furnaces, slag deposits, tuyere fragments, charcoal concentrations, and specialized working areas that revealed an unexpectedly advanced metallurgical industry operating long before Roman administration arrived. Chemical analysis of slag demonstrated repeated smelting of both iron and copper alloys, indicating that metal production was not an occasional household activity, but a permanent and organized industry. Producing workable iron requires furnace temperatures approaching 1200 degrees Celsius, conditions impossible to maintain without carefully controlled airflow, fuel management, and furnace geometry. Experimental archaeology has shown that even slight changes in oxygen supply dramatically affect bloom quality, yet the organic bellows, wooden supports, and leather equipment that once powered these furnaces disappeared long ago. What remains are only the vitrified furnace walls and metallic waste, proving that the technology functioned successfully. Researchers therefore understand the final products remarkably well, while still lacking direct evidence explaining exactly how craftsmen regulated combustion so consistently. Even more intriguing, metallurgical debris indicates repeated production over generations, implying that highly specialized technical knowledge survived through apprenticeship, despite the absence of written manuals or formal engineering texts. The settlement reveals another engineering achievement through a structure known as a Castro sauna, one of the most distinctive architectural traditions of northwestern Iberia. Unlike the monumental bathhouses later introduced by Rome, these buildings consisted of carefully arranged chambers where heated stones generated dense steam after water was poured onto their surfaces. Excavation identified stone-lined passages, combustion areas, and ventilation features that suggest deliberate control of airflow and temperature rather than simple heating. Archaeologists continue debating whether these facilities serve ritual purification, medical treatment, warrior initiation, or a combination of all three. Whatever their purpose, maintaining usable steam inside an enclosed stone chamber without filling it with dangerous smoke required practical knowledge of heat transfer, ventilation, and structural durability that exceeded what is usually associated with small Iron Age communities. Water management throughout Chaucer-Martin presents another unresolved puzzle. Mountain settlements normally suffer from rapid runoff capable of undermining foundations and triggering landslides, especially under the high annual rainfall typical of Atlantic Spain. Excavations instead revealed channels, drains, and carefully graded surfaces directing water away from buildings before it could accumulate beneath retaining walls. Modern hydraulic engineering recognizes that even small errors in drainage design eventually produce catastrophic structural failure. Yet many of these systems continued functioning for centuries. Because almost all measuring tools were made from perishable materials, archaeologists still cannot determine how builders established consistent gradients across irregular terrain with such remarkable precision. The organization of the settlement itself also challenges traditional assumptions about Iron Age societies. Residential buildings, industrial workshops, defensive sectors, and ceremonial spaces occupy distinct areas, connected through an orderly circulation network rather than developing randomly over time. This pattern suggests coordinated planning extending beyond individual households into community-wide decision-making. Similar planning principles appear elsewhere across the Castro culture, but Chaucer Martin preserves them with exceptional clarity because successive occupations remained remarkably well stratified. Even so, the identity of the planners remains completely unknown. No inscriptions record political leaders, architects, or master builders responsible for organizing construction on such a scale. The history of the settlement took an unexpected turn during the Roman period, when it continued to prosper instead of disappearing immediately after conquest. Imported ceramics, Roman goods, and changing architectural styles demonstrate integration into the imperial economy while preserving elements of local tradition. That continuity ended abruptly during the 2nd century AD, when geological evidence indicates that a powerful earthquake likely damaged the settlement beyond recovery. Collapsed walls, crushed structures, and sudden abandonment preserved entire sections beneath layers of debris, creating an archaeological time capsule that has allowed researchers to reconstruct technologies normally erased by later rebuilding. Perched above the Alhama River in La Rioja, northern Spain, Contrebia-Lucard may at first seem like just another ruined Iron Age hill fort, yet beneath its weathered cliffs lies one of the most remarkable engineering landscapes created by the Celtiberians. Long before Roman rule reached this region, an entire fortified city was carved directly into living sandstone, leaving behind construction methods that archaeology can describe but still cannot fully explain. The ruins were known locally for centuries, but systematic archaeological investigation only began during the 20th century, with extensive excavations from the 1970s onward, revealing streets, defensive systems, reservoirs, dwellings, and public spaces preserved beneath accumulated sediment. Stratigraphic analysis, ceramic typology, and Roman historical sources indicate that the settlement flourished between approximately the 4th century BCE and the 1st century BCE, before gradually declining after Roman control of the region became firmly established. Every excavation season has exposed additional evidence that the visible ruins represent only part of a far larger urban plan, concealed within the rock itself. What immediately separates Contribia-Lucade from nearly every other Celtiberian settlement is that its builders did not simply construct on top of a mountain, they reshaped the mountain into the city. Instead of leveling the summit with imported fill or raising massive masonry platforms, they transformed the natural sandstone bedrock into streets, stairways, building foundations, storage chambers, drainage channels, and defensive features by removing enormous quantities of solid rock. Modern archaeologists can measure the finished surfaces with remarkable precision, but they still cannot reconstruct exactly how Iron Age engineers achieved such extensive modification using the technology available more than 2,000 years ago. Sandstone is softer than granite, yet it remains a durable sedimentary rock that demands sustained labor, accurate planning, and effective tools to produce long, flat surfaces across an entire settlement. This raises one of the site's greatest mysteries. Every street appears to belong to a coordinated urban design rather than centuries of random expansion. Pathways connect residential districts with storage areas, defensive sectors and water facilities while following gradients that remain practical even today. Such organization suggests that the builders possessed a comprehensive master plan before excavation even began. Unlike Roman colonies, however, no written plans, surveying manuals, or administrative records survive to explain how measurements were transferred across the irregular mountain surface. Historians assume that ropes, wooden stakes, simple leveling instruments, and accumulated practical experience guided the work, yet none of these temporary construction systems have survived in the archaeological record. What remains is the finished geometry, while the engineering process itself has almost completely disappeared. As researchers continued examining the settlement, another remarkable achievement emerged from beneath the rock. Much of the city's infrastructure was integrated directly into the same sandstone mass, instead of being added afterward. Reservoirs, cisterns, wells, and narrow channels were carefully carved into the bedrock to collect and distribute water throughout the settlement. Northern Spain experiences highly seasonal rainfall, making reliable storage essential for survival during dry periods and prolonged military sieges. Hydrological studies indicate that several channels were designed with gradients gentle enough to maintain water flow while minimizing erosion, demonstrating practical knowledge of hydraulic behavior. Although the principles involved can be explained scientifically today, archaeologists still debate how Iron Age builders calculated these gradients across an uneven landscape without modern surveying equipment. Their success becomes even more impressive because portions of the drainage network continue directing rainwater efficiently after more than 2 millennia of natural weathering. The defensive system surrounding Contrebia Leucidae adds another layer to the engineering puzzle. Rather than relying solely on masonry walls, the inhabitants excavated a monumental rock-cut ditch separating vulnerable approaches from the fortified plateau. Archaeological surveys estimate that this trench extended for nearly 700 meters, reaching widths of roughly 8 to 9 meters and depths approaching 8 meters in some sections. Excavating such dimensions required removing tens of thousands of cubic meters of sandstone. Experimental archaeology demonstrates that iron chisels and hammers are capable of cutting sandstone, but reproducing a ditch of this scale would require an enormous labor force working continuously for years. Surprisingly, archaeologists have not identified equally massive spoil deposits nearby. The missing waste rock has generated several hypotheses. Some researchers believe much of the excavated material was reused for construction elsewhere within the settlement, while others suggest centuries of erosion dispersed the debris downslope. Neither explanation fully accounts for the quantity of stone that must originally have been extracted. Roman historians provide additional context for the city's formidable reputation. Titus Livius, better known as Livy, described campaigns in Celtiberia during the 2nd century BCE in which fortified settlements repeatedly resisted Roman armies, despite their superior military organization. Although historical accounts must always be interpreted carefully, archaeological evidence confirms that Contrebia Leucidae possessed one of the most sophisticated defensive layouts in the region. Attackers approaching the settlement would have encountered narrow access routes, elevated observation points, steep natural cliffs, and the immense rock-cut ditch before reaching the main fortifications. The surrounding landscape itself became part of the defensive architecture, demonstrating an understanding that terrain could be engineered as effectively as walls. Equally fascinating is the city's sophisticated approach to controlling water during storms. Rain falling across the plateau did not simply erode buildings or accumulate unpredictably. Instead, carefully carved channels redirected runoff toward designated collection points while protecting residential areas from destructive flooding. Modern geomorphological analysis shows that erosion patterns around many excavated sectors remain surprisingly limited considering more than 2,000 years of exposure. Such preservation reflects not only the durability of sandstone but also the effectiveness of the original drainage design. Whether these systems resulted from generations of practical experimentation or from highly specialized engineering knowledge, passed between craftsmen remains unknown because no written Celtiberian technical texts have ever been discovered. Construction logistics remain perhaps the most difficult question of all. Every surface visible today represents the final stage of an immense engineering project, yet almost every temporary element required to complete that project has vanished. Wooden scaffolding decays, rope disappears, measuring stakes rot, and earthen working platforms erode into the landscape. Archaeologists, therefore, study negative evidence, attempting to reconstruct vanished construction methods solely from finished stonework. Tool marks preserved on some carved surfaces indicate repeated impact from iron implements, but they cannot reveal workforce organization, construction schedules, or management techniques. Large-scale public works require planning, food supplies, skilled supervision, and coordinated labor, suggesting that Contribia Lucard possessed a social organization considerably more sophisticated than its surviving material culture alone might imply. Excavations found imported pottery, local ceramics, metal items, and other objects, showing the city was part of wide trade networks across Iberia and the Western Mediterranean. Its people weren't isolated, but trade alone doesn't explain why its engineering is so different. While rock-cut features exist elsewhere, nowhere else forms a whole city carved so deeply into stone, leaving the origins of this knowledge still unclear. On a fortified hill above the Navia River Valley in western Asturias, northern Spain, the ruins of Castro de Coana preserve one of the clearest surviving examples of an Iron Age settlement in Atlantic Europe. Known locally as the Castellón de Vilacondide, the site was already mentioned as an ancient ruin in 1818, but systematic investigation began in 1877, when José María Flores excavated more than 20 structures in what became the first formally studied hill fort in Asturias. Antonio García y Bellido and Juan Uria returned between 1940 and 1944, followed by further campaigns directed by Francisco Jorda from 1959 to 1961. What emerged was not a loose cluster of primitive huts, but a densely organized fortified community whose engineering had been underestimated for generations. Early researchers once believed that Coana had been founded after Rome conquered northwestern Iberia, largely because Roman pottery, coins, and other objects appeared among the ruins. Later excavations changed that chronology. Archaeological evidence now shows that the hill had already been fortified by at least the 5th century BC, centuries before the final Roman campaigns in northern Hispania between 29 and 19 BC. Occupation continued and changed under Roman influence, making Coana not a monument from a single moment, but a settlement repeatedly rebuilt over several centuries. This long sequence complicates almost every attempt to understand its technology, because walls, houses, and streets belonging to different phases were repaired, altered, and reused without leaving written plans. The excavated settlement is divided into 2 principal zones. At the summit stands a large oval enclosure, usually described as an acropolis, protected by a substantial defensive wall. Below it, the northern quarter contains more than 80 surviving buildings connected by narrow passages, paved areas, and small open spaces. Most houses are circular or oval, while several later constructions adopt more angular plans, associated with changing social and Roman architectural traditions. The compact arrangement initially appears irregular, yet the buildings do not simply occupy every available space. They were fitted into the slope through retaining walls, step foundations, and carefully controlled circulation routes, creating a settlement whose organization responded precisely to the shape of the hill. This adaptation is one of Coana's deepest engineering puzzles. The builders had no concrete foundations, steel reinforcement, or modern instruments for calculating soil pressure. yet they established dozens of stone structures on uneven ground, exposed to persistent Atlantic rainfall. Each platform had to carry the weight of masonry walls, timber roofs, stored materials, and human activity without sliding downhill. Instead of cutting the entire hill into a regular grid, the builders used the natural contours, placing walls where the ground offered support and adding terraces where level surfaces were required. The result suggests generations of practical knowledge concerning drainage, load distribution, and slope stability, although no measuring device, technical text, or construction drawing has been recovered. The walls themselves reveal how this knowledge worked. Koana was built primarily from locally available stone laid without mortar. Stability depended on the contact between irregular pieces, the weight of the masonry, and the careful arrangement of inner and outer wall faces around a packed core. Such dry stone construction can tolerate small movements because individual stones shift slightly instead of forcing the entire wall to crack as a rigid mass. It can also allow rainwater to pass through rather than building destructive pressure behind retaining structures. These properties help explain the survival of substantial sections for more than 2,000 years, but they do not reveal how ancient builders selected each stone, judged the correct wall thickness, or recognized unstable sections before failure occurred. This problem becomes more striking in the defensive zone. The upper enclosure was not protected by a symbolic boundary, but by a strong wall controlling the most important ground above the settlement. Constructing it required quarrying, moving, and positioning large quantities of stone on a hill where wheel transport would have been difficult. No ancient cranes, permanent ramps, or transport vehicles have been found at Koana. Wooden sledges, rollers, levers, ropes, and coordinated labor offer plausible explanations, but they remain reconstructions based on comparable ancient technologies rather than direct evidence from the site. The finished fortification survives, while most of the temporary machines and wooden structures needed to build it disappeared completely. Rain created an equally serious challenge. Western Asturias has a humid Atlantic climate, and uncontrolled runoff would have entered houses, softened earthen floors, and undermined terraces. Koana contains no monumental sewer system comparable to those of Roman cities, yet the settlement endured repeated wet seasons for centuries. Its drainage appears to have depended on the combined effects of sloping lanes, permeable masonry, raised thresholds, narrow channels, and gaps between structures. Instead of collecting all water in a single engineered conduit, the settlement seems to have divided the flow into smaller paths directed around buildings and downhill through the street network. Archaeologists can identify parts of this system, but later erosion and reconstruction make it difficult to recover the complete hydraulic plan or determine whether it was designed from the beginning or improved gradually after observing floods. The circular houses present another example of apparently simple architecture concealing complex decisions. A curved wall distributes roof loads without the weak corners found in poorly constructed rectangular buildings, while a conical timber and thatch roof can transfer weight relatively evenly around the circumference. The shape also resists strong winds from multiple directions, an advantage in an exposed landscape. Yet circular construction creates practical problems of its own. The builders had to maintain a consistent radius without modern surveying tools, position doorways without weakening the wall, and shape timber roofs so that forces remained balanced. The repeated appearance of buildings with comparable forms suggests shared building rules, but archaeologists have found no standard measuring rod or marked unit that would reveal how dimensions were controlled. The houses are also densely packed, sometimes separated by passages barely wide enough for movement. This arrangement reduced the length of defensive walls required to protect the population and may have limited exposure to wind, but it increased the danger of fire and made runoff more difficult to control. The builders therefore had to coordinate individual houses with the larger settlement, rather than treating each structure as an isolated project. Doorways faced selected lanes. Walls avoided blocking circulation, and open areas were retained where domestic or communal work could take place. Such consistency implies organized decision-making, yet Koana has produced no palace, archive, or administrative building that clearly identifies who imposed these rules. The most technically unusual structures lie close to the entrance of the settlement, where archaeologists uncovered two buildings commonly interpreted as Castro saunas or steam baths. Related monuments appear in a limited zone of northwestern Iberia and are considered highly distinctive within European Iron Age archaeology. Their interiors were divided into spaces associated with heating, steam, and controlled movement, while stone construction helped retain temperature and withstand repeated exposure to moisture. The interpretation as steam baths is widely accepted, although their social meaning remains disputed. They may have served ritual purification, initiation, healing, or communal ceremonies rather than ordinary hygiene alone. Operating such a building required more than placing hot stones in a room. Fuel had to be burned without filling the occupied chamber with intolerable smoke. Heat had to pass into the bathing area, and steam needed to remain long enough to produce the intended effect without condensing immediately on cold surfaces. Openings, wall thickness, and the sequence of chambers would have influenced air circulation and temperature. Because timber roofs, doors, and internal fittings have vanished, the surviving masonry represents only part of the original machine. Modern reconstructions can explain how the bath may have functioned, but they cannot determine exactly where fires were maintained, how much water was introduced, what temperatures were reached, or how operators controlled the process. Koana also preserves evidence of ironworking, stoneworking, and other crafts, activities that demanded controlled supplies of raw material and fuel. Iron production required temperatures exceeding ordinary domestic fires, while forging depended on repeated heating and skilled control of airflow. Metal tools would have been essential for woodworking, agriculture, warfare, and the maintenance of buildings, yet the organization of production remains uncertain. Workshops may have served individual households, specialist families, or a broader authority, but the physical evidence is too incomplete to show how labor was divided or how technical knowledge moved between generations. Perched almost 100 meters above the Bay of Biscay near modern Gijón in Asturias, northern Spain, La Campa Torres appears at first to be another Iron Age hill fort overlooking the Atlantic. Yet beneath its windswept cliffs lies evidence of engineering decisions so sophisticated that archaeologists are still debating how an indigenous community, more than 2,000 years ago, transformed an exposed rocky headland into one of the strongest fortified settlements along the Cantabrian coast. The site remained hidden beneath later occupation until systematic archaeological excavations began during the 1980s, after surveys identified prehistoric pottery, defensive earthworks, and structural remains scattered across the headland. Excavations revealed continuous occupation beginning around the Late Bronze Age, with major expansion during the Iron Age by the Astures before the Romans established military and commercial facilities on the same promontory after the Cantabrian Wars. Stratigraphic analysis, radiocarbon dating of organic remains, imported ceramics, and Roman materials consistently placed the principal indigenous settlement between approximately the 4th and 1st centuries BC, confirming that its most remarkable engineering achievements predated direct Roman administration. Once the settlement emerged from the ground, researchers realized that its greatest achievement was not the massive walls themselves, but the extraordinary way the builders adapted every structure to an unforgiving landscape. The headland consists of fractured sandstone and quartzite continuously exposed to Atlantic storms, salt spray, intense rainfall and powerful winter winds that frequently exceed 100 kilometers per hour. Building permanent fortifications on such terrain would normally accelerate erosion and structural instability, yet substantial sections of defensive walls, terraces, and building platforms have survived for more than 2 millennia. Geological studies indicate that the builders repeatedly cut directly into bedrock before laying foundations, reducing differential settlement while using the natural contours to distribute structural loads instead of fighting against the terrain. Although modern engineers can explain why these solutions work mechanically, archaeologists still cannot determine how Iron Age builders acquired such practical geological knowledge without written engineering traditions or surviving technical manuals. The defensive system itself demonstrates an equally impressive understanding of terrain. Excavation has revealed multiple defensive components, including ditches, ramparts, stone walls, and carefully controlled entrances that forced anyone approaching the settlement to climb uphill while repeatedly changing direction. Modern battlefield analysis recognizes this arrangement as an effective method for reducing the momentum of attacking forces while maximizing the advantage of defenders occupying higher ground. Computer-based visibility studies conducted on similar Atlantic hillforts have shown that elevated coastal settlements could monitor extensive stretches of shoreline, allowing early detection of ships long before they reached land. La Campa Torres occupies exactly such a commanding position, suggesting that its builders selected the location not only for defense, but also for surveillance of maritime traffic across the Bay of Biscay. Whether this strategic placement resulted purely from accumulated experience or from systematic observation remains impossible to determine, because no written records survive from the astures themselves. As excavation expanded across the interior, however, archaeologists encountered a mystery that continues to attract particular attention. Instead of houses appearing randomly wherever space permitted, many residential structures occupy remarkably consistent plots arranged according to repeated spatial patterns. Individual buildings differ in detail, yet their dimensions, spacing, and orientation display a surprising degree of regularity, despite the irregular shape of the rocky plateau. Excavation plans reveal that walls frequently align along common axes, while open spaces between buildings remain relatively uniform, even where the terrain changes dramatically. Such consistency strongly suggests that construction followed predetermined planning principles rather than spontaneous expansion over generations. This apparent modular urban planning raises difficult questions because none of the tools normally associated with standardized surveying have been discovered. No measuring rods, calibrated markers, engraved plans, or written instructions have been recovered from the site. Nevertheless, repeated architectural proportions indicate that builders probably relied on standardized units transmitted through practical tradition. Experimental archaeologists have demonstrated that simple measuring cords tied with regularly spaced knots can achieve surprisingly high precision across large construction projects, yet no direct evidence confirms that such techniques were employed at La Campa Torres. If flexible cords, wooden templates, or organic measuring devices form the basis of construction, they would have disappeared completely in the humid Atlantic environment long before excavation began. The settlement, therefore, preserves the finished geometry, while the instruments that created it have vanished, leaving only the pattern itself as indirect evidence of an organized planning system. The implications extend beyond architecture alone. Standardized plots suggest coordinated allocation of space, implying that someone possessed authority to determine where houses could be built before construction even began. Such organization reflects a level of social administration far more sophisticated than older interpretations of loosely organized Iron Age tribal communities. Similar planning principles have been identified at several major castros across northwestern Iberia, yet each settlement applies them differently according to local topography. This combination of standardization and adaptation hints at an engineering tradition capable of balancing fixed construction rules with changing geological conditions. Exactly how this knowledge was taught remains unknown because the Astures left virtually no written documentation explaining their building practices. Water management presents another unresolved engineering challenge. Asturias receives well over 1,000 millimeters of rainfall annually, creating continuous risks of erosion on exposed coastal slopes. Without effective drainage, heavy seasonal rain would gradually undermine retaining walls and destabilize occupied terraces. Surprisingly, excavation has revealed relatively limited evidence of catastrophic slope failure during the principal occupation period. Archaeologists believe the builders probably incorporated shallow drainage channels, permeable stone layers, and carefully controlled surface gradients that redirected runoff toward natural fissures within the bedrock. Most of these hydraulic features would have consisted partly of earth, timber, or other biodegradable materials that disappeared centuries ago, making complete reconstruction impossible. The remarkable preservation of structural foundations nevertheless indicates that water was managed far more effectively than previously assumed for communities lacking Roman hydraulic technology. Construction logistics introduced another enduring mystery. Thousands of stone blocks had to be extracted, transported across uneven ground, and positioned accurately on steep slopes where wheeled vehicles would have been of limited practical use. Archaeologists propose combinations of wooden sledges, rollers, rope systems, levers, and coordinated human labor because comparable techniques are documented elsewhere in prehistoric Europe. Even so, no quarry infrastructure, hauling ramps or construction equipment has been identified at La Campa Torres itself. The finished architecture survives, while the temporary engineering systems responsible for creating it disappeared almost without trace, forcing researchers to reconstruct the entire construction process through comparison rather than direct evidence. Excavations also uncovered iron slag, metallurgical debris, and evidence of local metalworking, demonstrating that the settlement functioned as more than a military stronghold. Iron production requires furnace temperatures approaching 1200 degrees Celsius, together with carefully regulated airflow and controlled charcoal quality. Although these technological requirements are well understood today, the furnaces themselves survive only in fragmentary condition, preventing archaeologists from determining exactly how local craftsmen maintained stable temperatures or organized repeated production cycles. The existence of successful metallurgy nevertheless confirms that sophisticated practical knowledge extended beyond architecture into industrial processes. In the mountains of southwestern China, archaeologists uncovered the remains of 3 political centers that had once controlled vast territories without functioning as ordinary imperial cities. Laoxicheng lies beside the Lingxi River in Yongshun County, Hunan. Tangya stands in Jianfeng County, Hubei, and Heilongtun occupies a fortified mountain position near Zunyi in Guizhou. Excavations revealed administrative compounds, roads, tombs, drainage channels, defensive walls, and monumental gateways belonging to hereditary regional rulers known as Tusi. Together, the 3 sites cover more than 780 hectares and were added to the UNESCO World Heritage List in 2015. Yet the buildings they left behind raise a difficult question. How were complex cities and fortresses engineered across some of China's most unstable and inaccessible terrain? The Tusi were local hereditary leaders recognized by successive Chinese governments, particularly during the Yuan and Ming periods. They governed minority populations while formally accepting imperial authority, creating political centres that combined local building traditions with architectural ideas associated with the central China. Lao Zicheng served the Pang rulers for nearly 6 centuries, while Tangya became the capital of the Qin domain during the 14th century. Heilongtun was different. Built as the military centre of the powerful Bozhou chiefdom, it became a mountain fortress, whose ruins preserve one of the clearest examples of terrain-based defensive engineering in the region. Heilongtun was established in the 13th century on Longyan Mountain, at an elevation of approximately 1,300 meters. The fortified area covered roughly 1.5 square kilometers, while walls and defensive lines extended for several kilometers across ridges surrounded by cliffs. Access was restricted through a sequence of gates positioned along narrow approaches. Historical and archaeological evidence indicates that the fortress was destroyed in 1600, when Ming forces defeated the Bozhou rebellion, but large sections of the stone infrastructure survived the assault, fire, vegetation, and more than 4 centuries of erosion. The survival of these structures begins with geology. Heilongtun stands in a karst landscape where limestone is fractured by joints, underground cavities, and water erosion. Such terrain offers natural protection, but it is not automatically suitable for heavy construction. A wall placed above a hidden fracture can settle unevenly, while rain entering cracks can weaken foundations and trigger slope failure. The builders therefore had to distinguish stable rock from weathered surfaces before positioning gates, retaining walls, and elevated compounds. Archaeology reveals the completed structures, but no surviving survey instruments, construction manuals, or detailed engineering records explain how those decisions were made. This uncertainty becomes more striking when the defensive layout is examined as a single system. Heilongtun contained 9 principal passes, traditionally described as 6 on the eastern approach and 3 on the western side. They were not arranged as identical gateways along a regular perimeter. Instead, each was fitted into a different section of the mountain, forcing attackers through steep climbs, narrow turns, and enclosed spaces before they could approach the inner compound. The walls did not simply separate the fortress from the landscape. They converted cliffs, ridges, and ravines into parts of the fortification itself. Designing such a system required accurate knowledge of visibility, movement, and range. A gate placed only a few meters too far forward could create a blind area, while a poorly supported wall could collapse under its own weight or under the pressure of wet soil behind it. The irregularity of the terrain meant that builders could not repeat a single standard plan. Every section required separate adjustment, yet the surviving layout suggests that these adjustments formed a coordinated defensive sequence rather than a collection of unrelated barriers. What remains unclear is whether that coordination was established through measured plans, scale models, inherited rules of construction, or continuous decisions made directly on the mountain. The movement of stone presents an even more physical mystery. Walls, gates, stairs, and foundations required enormous quantities of limestone. Some material could be extracted locally, reducing horizontal transport, but quarrying near the building area created another problem because removing too much rock could destabilize the ground supporting the fortifications. Blocks then had to be shaped, lifted, and positioned on steep slopes where wheeled vehicles would have been of limited use. Wooden sledges, rollers, ropes, lever systems, and temporary ramps are all technically plausible, yet the temporary structures needed for such operations have left little archaeological evidence. Transporting stone was only one part of the challenge. Large construction projects also required timber, lime, metal tools, water, and food for a concentrated labor force. At more than 1,000 meters above sea level, every worker and animal consumed supplies that had to climb the same restricted routes used for building materials. Storage had to be protected from rain and spoilage, while construction schedules had to account for seasonal weather. The fortress demonstrates that such a logistical system existed, but the administrative records needed to reconstruct its scale, labour organisation and rate of construction have not survived. Water was both essential and dangerous. Southwestern China receives substantial seasonal rainfall, and mountain surfaces can rapidly direct runoff toward walls and courtyards. Without controlled drainage, water pressure builds behind retaining structures, soil becomes saturated, and foundations begin to move. The Tusi sites preserve drainage ditches, culverts and channels integrated with roads and architectural compounds. Tangya is especially important because its surviving remains include boundary walls, paved roads, and drainage installations that reveal how water management formed part of the urban plain, rather than being added only after construction. At Laoxicheng, the engineering problem was different but equally complex. The city developed beside a river within a mountainous valley and contained administrative, residential, ceremonial and burial zones, connected by an organized network of streets. Its core archaeological area covers more than 250,000 square meters, while the wider cultural landscape extends across approximately 25 square kilometers. Excavated remains include streets, city walls, temples, tombs, monumental arches and drainage systems, indicating that Laoxicheng functioned as a carefully structured capital rather than a loosely assembled mountain settlement. Building beside a river provided water and transport, but it also exposed the city to flooding, erosion and sediment movement. Roads had to follow the slope while remaining passable, and channels needed sufficient gradient to remove runoff without cutting into foundations. If their angle was too shallow, sediment would accumulate and block the system. If it was too steep, fast-moving water could erode the channels themselves. The preserved drainage network shows that the builders understood these practical relationships, although archaeologists cannot determine whether flow was estimated through formal calculation or through generations of observation. The organization of Laoxicheng adds another unresolved dimension. Its roads and compounds adapted to the valley instead of imposing a perfect rectangular grid. Administrative buildings occupied prominent positions, while ritual areas, residential quarters and elite tombs were separated yet connected. This required more than architectural skill. The planners had to predict how people, goods, animals and water would move through a confined landscape over long periods. The city appears to have grown across several phases, but researchers still face the problem of distinguishing an original master plan from a system that became coherent through repeated expansion. Tangya provides a smaller comparison. Built during the 14th century, it represented a lower-ranking Tusi domain and occupied a more modest area than Laoxicheng or Heilongtun. Even so, excavations revealed an administration zone, stone roads, boundary structures, tombs, drainage ditches and monumental remains. The difference in scale is valuable because it suggests that certain planning principles were not limited to the wealthiest rulers. Smaller domains also used durable stone infrastructure and organized water control, raising the possibility that Tusi builders shared technical traditions across political boundaries. However, similarities do not prove that the same engineers worked at all the three places. Local geology, ethnic traditions, and political rank produced clear architectural differences. Heilongtun was dominated by military defense, Laoxicheng by the functions of a regional capital, and Tangya by a more compact administrative order. The unanswered question is whether these sites followed a common body of technical knowledge, or whether comparable solutions emerged independently because builders faced similar environmental pressures. In 1800, British surveyor Colin Mackenzie began documenting the ruins of Vijayanagara at Hampi in the present-day Indian state of Karnataka. Among the remains inside the royal centre stood an enormous terraced platform later identified with a ceremonial structure described by 16th century Portuguese visitors. Today it is known as the Mahanavami Dibba, the great platform from which Vijayanagara's rulers displayed imperial power before thousands of spectators. The surviving monument rises more than 10 metres above its surroundings and consists of 3 ascending levels, each faced with carefully assembled masonry and bands of carved reliefs. Its position was deliberately commanding. The platform occupied one of the highest points in the royal zone, overlooking spaces where processions, military reviews, animal displays, dances, and ceremonial gatherings could take place. Yet what visitors see today is only the stone base. Archaeological interpretation suggests that a pillared wooden pavilion once stood on the summit, but almost every trace of that superstructure disappeared when Vijayanagara was conquered and devastated in 1565. The engineering puzzle therefore begins with an incomplete building whose most important upper section has vanished. The platform was not constructed in a single operation. Architectural analysis indicates at least 3 major building phases extending across the Vijayanagara period. Earlier masonry was enlarged, covered or incorporated into later additions, producing the stepped mass visible today. This means its builders were not working from an empty site. Each expansion had to carry new weight while preserving the stability of the structure beneath it. Without reinforced concrete, steel, framing, or modern geotechnical instruments, they created a platform that has remained standing for roughly 5 centuries despite monsoon rain, vegetation, stone removal, and the violent destruction of the royal capital. Exactly how the internal mass was organized remains less obvious than the external terraces suggest. The visible walls are not proof that the entire monument consists of solid, uniformly laid stone. Monumental platforms of this type could contain rubble packing, earth, secondary masonry, and retaining walls arranged in separate construction compartments. Such systems reduce the quantity of dress stone required, but they introduce another difficulty. Loose material can settle, absorb water, or push outward against the facing. The builders therefore needed to control both vertical loading and lateral pressure across a structure tens of meters wide. The platform's broad base, inward stepping profile, and thick retaining surfaces would have spread its weight gradually toward the ground. Yet no surviving Vijayanagara manual explains the calculations, construction sequence, or foundation preparation used here. The choice of material made the work even more demanding. Hampi lies within a landscape dominated by granite outcrops and immense weathered boulders, giving the builders access to durable local stone but not to material that was easy to shape. Granite is rich in hard minerals such as quartz and feldspar and cannot be carved as quickly as softer sandstone or limestone. Vijayanagara masons nevertheless produced long courses, stairways, mouldings, and extensive sculptural panels across the platform. Their likely tools included iron points, chisels, hammers and wedges, while repeated dressing and abrasion refined the surfaces. These methods are technically plausible and are consistent with wider South Indian stoneworking traditions, but archaeology has not reconstructed the precise division of labour or the time required to complete the platform's enormous carved exterior. The difficulty was not simply cutting individual blocks. Every piece had to enter a coordinated building sequence. Quarry workers first located stone without fractures severe enough to compromise it. Teams then separated blocks along natural weaknesses or prepared wedge lines, reduced unnecessary mass near the quarry, and transported the stone toward the royal centre. Even when the source lay nearby, moving multi-ton granite across uneven ground required prepared routes, timber supports, ropes, sledges, carts, or teams of draft animals. Elephants may have contributed pulling power, but popular images of elephants effortlessly lifting finished blocks oversimplify the problem. The heavier task was controlling movement so that stone did not accelerate, tilt, or crush the equipment beneath it. Raising blocks onto successive terraces presented another challenge. The most practical explanation is the use of temporary earthen ramps combined with levers and hauling systems, techniques known across many pre-industrial building traditions. Yet no intact construction ramp survives beside the Mahanavami Dibba, and no contemporary illustration shows the platform under construction. Because temporary works were normally dismantled and their materials reused, the finished monument preserves the result while concealing the infrastructure that produced it. This is not evidence of unknown machinery, but it leaves the exact logistical system unconfirmed. The platform stairways reveal how carefully circulation was integrated into the monument. Access was provided from more than one direction, but these approaches were not simple utility stairs. They controlled how rulers, attendants, and ceremonial participants moved between levels, transforming physical elevation into a political performance. A king ascending above the crowd became visible from a great distance, while those approaching him were forced through predetermined routes. The architecture therefore functioned simultaneously as a load-bearing structure, a viewing platform, and a machine for organizing human movement. This interpretation is strengthened by the account of Domingo Paes, a Portuguese visitor who observed Vijayanagara during the reign of Krishna Devaraya in the early 16th century. Paes described elaborate Mahanavami celebrations involving troops, horses, elephants, dancers, musicians, nobles, and royal ritual. The correspondence between these written descriptions and the reliefs carved around the platform is striking. Rows of elephants, mounted riders, hunters, warriors, acrobats, and performers turn the stone base into a permanent representation of ceremonies once staged around it. Yet the carvings create a technical mystery of their own. The scenes stretch across different construction levels and appear to have been produced by several groups of sculptors, perhaps at different times, maintaining horizontal registers, repeated proportions, and a coherent visual rhythm required more than individual artistic skill. Supervisors must have established reference lines, panel dimensions, and sequences before detailed carving began. Some reliefs were probably worked after blocks had been placed, while others may have been partly prepared on the ground. Distinguishing these stages from tool marks and unfinished surfaces is difficult, because centuries of weathering have softened many details. The imagery also suggests that the craftsmen were documenting a cosmopolitan imperial capital, rather than inventing a purely symbolic world. Camels, foreign-looking attendants, imported horses, and varied clothing styles reflect Vijayanagara's connection to commercial networks extending through the Indian Ocean and the Deccan. Horses were especially important because high-quality war animals had to be imported into southern India, where climatic conditions limited large-scale breeding. Their repeated appearance on the monument was therefore both decorative and political, advertising the empire's ability to command distant trade, military resources, and specialized knowledge. Water management forms another essential part of the engineering context. The Mahanavami Dibba did not stand alone, but belonged to a carefully organized royal landscape containing tanks, channels, drains, and ceremonial water structures. Archaeological work near the platform uncovered a precisely constructed stepped tank supplied by a stone aqueduct. Surveys across the wider Vijayanagara metropolitan region also identified wells, cisterns, and hydraulic installations serving domestic, agricultural, ritual, and public needs. These discoveries demonstrate that the royal centre was integrated into a planned water network rather than dependent only on natural runoff. For the platform itself, drainage was crucial. A structure with broad horizontal surfaces exposed to seasonal monsoon rainfall could not safely allow water to penetrate its packed interior. Saturated fill would become heavier, encourage settlement, and increase outward pressure on retaining walls. The builders therefore had to shape surfaces, joints, and surrounding ground so that rainwater escaped before causing serious damage. The survival of the main mass suggests that these measures were broadly effective, but the original drainage arrangement cannot be reconstructed completely because upper pavements, wooden structures, and adjoining buildings have disappeared. The greatest missing element remains the pavilion that once stood above the stone terraces. Post sockets and comparisons with other Vijayanagara buildings indicate that the summit probably supported columns and a roof, creating a shaded ceremonial space for the ruler and his court. Because wood is lighter than stone, it allowed a large upper structure without placing impossible loads on the platform. It was also vulnerable to fire. When the city was attacked after the Battle of Talikota, palace buildings with timber columns, beams, and roof systems could be burned even when their stone foundation survived. What now appears to be an open monument was once only the lower skeleton of a far more complex architectural composition. El Carameno, located in the highlands of Guadalajara province in central Spain, appears at first glance to be nothing more than the remains of a small Celtiberian hilltop village. Yet beneath its weathered stones lies one of the most surprising engineering puzzles of Iron Age Europe, where a settlement built more than 2,500 years ago displays a level of planning and construction that still raises difficult archaeological questions. El Carameno was identified during archaeological surveys in the 1970s, and systematic excavations led by Spanish archaeologists during the following decades revealed an exceptionally well-preserved Celtiberian settlement dating mainly between the 6th and 3rd centuries BC. Unlike many Iberian sites that evolved gradually over centuries, the excavation exposed complete houses, defensive walls, streets, workshops, storage areas, and even evidence of the settlement's final destruction by fire. Radiocarbon dating, ceramic typology, and imported artifacts consistently place the main occupation within the early and middle Iron Age, making El Carameno one of the best preserved examples of Celtiberian domestic architecture ever excavated. What immediately attracted archaeologists was not the size of the village, but the remarkable regularity of its design. Instead of expanding randomly as families added new buildings over generations, the settlement appears to have been conceived almost as a complete project before construction even began. Houses occupy orderly positions along carefully organized streets. Walls share common structural alignments, and many buildings follow nearly identical dimensions. Such uniformity is highly unusual for communities of this period, especially in inland Iberia, where settlements generally developed organically in response to local needs. Excavation plans suggest that the builders first established an overall layout before individual houses were constructed, implying the existence of centralized planning. The mystery begins here because no written records survive, no measuring instruments have been recovered, and no construction manuals exist to explain how Celtiberian builders achieved such consistency. Archaeologists have proposed that standardized ropes, wooden measuring rods, or carefully repeated body-based units may have been employed, but direct evidence for any of these methods has never been discovered, leaving the planning process itself almost entirely invisible. This carefully organized layout becomes even more impressive when the surrounding terrain is considered. El Carameno occupies uneven ground where natural slopes would normally complicate construction, yet the settlement maintains remarkably stable building platforms. Excavation beneath several houses revealed layered foundations consisting of large stones, supporting progressively smaller stones and compacted earth above them. This combination distributed structural loads while allowing limited movement of the ground beneath seasonal changes in moisture. Modern geotechnical engineering employs similar principles when stabilizing buildings, on uneven terrain, although using completely different materials. The ancient builders clearly understood that simply placing walls directly onto the surface would eventually lead to cracking or collapse. Whether this knowledge resulted from generations of accumulated experience or from techniques exchanged across wider Mediterranean networks remains uncertain, because no contemporary text describes Celtiberian engineering practices. As archaeologists continued exposing entire domestic blocks, another sophisticated feature emerged inside the architecture itself. Several buildings appear to incorporate thick composite walls or double-layered stone construction that created pockets of trapped air between structural elements. Thermal studies of traditional stone architecture demonstrate that such designs reduce daily temperature fluctuations by slowing heat transfer through the walls. During cold winters common on the Spanish plateau, stored heat from interior hearths would have remained inside longer, while during hot summer afternoons the massive stone exterior delayed the penetration of solar heat. Although similar thermal principles are recognized in modern passive building design, determining whether Iron Age builders intentionally optimized insulation or simply arrived at this solution through experience remains impossible, because no written explanation accompanied the architecture they left behind. The sophistication continues beneath the streets, where another engineering problem had to be solved without modern drainage systems. Seasonal rainfall across central Spain can quickly saturate compacted soils, increasing erosion and threatening stone foundations. Surprisingly, archaeologists found no monumental drainage channels running through the settlement. Instead, subtle street gradients, carefully placed stone joints, and permeable gravel layers beneath floors appear to have guided water naturally away from occupied spaces. Hydrological modelling suggests that even slight differences in elevation could redirect runoff efficiently without requiring visible canals. Such solutions demanded an accurate understanding of local topography, because even small construction errors would have allowed water to accumulate inside houses. The drainage system therefore seems to have been integrated into the settlement's original plan, rather than added after problems developed, strengthening the argument that El Ceremeno was designed as a coherent engineering project from the very beginning. Evidence recovered from collapsed buildings also introduces questions about construction safety that remain difficult to answer. Excavation revealed extensive traces of burning associated with the settlement's destruction during the 3rd century BC, yet many stone walls survived standing while timber roofs collapsed inward. This pattern suggests that wooden structural elements were positioned in ways that limited catastrophic wall failure after fire. Some researchers believe the builders unintentionally created a primitive form of compartmentalized collapse in which combustible roofing failed before the heavier masonry lost stability. Others argue that the outcome simply reflects the inherent strength of dry stone construction rather than deliberate engineering. Because the original timber framework disappeared in the fire, only the surviving stone architecture remains available for analysis, preventing definitive conclusions. Construction materials themselves add another layer to the mystery. The settlement's stone blocks often display surprisingly consistent sizes, despite being quarried without iron machinery capable of industrial production. Standardized building elements would have greatly accelerated construction by allowing walls to be assembled with fewer adjustments during placement. Such uniformity hints at organized quarrying, careful transport, and coordinated labor rather than isolated household construction. Yet archaeologists have not identified large quarry workshops immediately associated with the settlement, nor have they recovered specialized stone-cutting installations capable of producing standardized blocks on a significant scale. The organization responsible for supplying these materials, therefore, remains largely invisible within the archaeological record. The upper sections of many buildings incorporated compacted earth above their stone foundations, introducing another unresolved technological question. Earthen walls are normally vulnerable to rain, frost, and erosion, yet portions of El Carameno survived for more than 2 millennia before excavation exposed them again. Laboratory analyses indicate carefully balanced mixtures of clay, sand, and fine gravel, producing material considerably stronger than ordinary soil. Some specialists suspect that organic fibers, plant material, or other natural stabilizers were originally mixed into the earth to improve durability, but nearly all organic compounds decomposed long ago, leaving no direct evidence of their composition. Without those missing ingredients, reconstructing the original manufacturing process remains largely speculative, despite modern laboratory testing. Daily life inside the houses reveals further evidence of practical engineering rather than simple shelter construction. Doorways were positioned to reduce exposure to prevailing winds, windows remained extremely limited, and central hearths occupied locations that distributed warmth throughout interior spaces while allowing smoke to dry wooden roofing materials. Experimental reconstructions based on excavated floor plans suggest that these arrangements produce surprisingly stable indoor temperatures despite the harsh, seasonal climate of inland Spain. Such efficiency reflects generations of accumulated environmental knowledge, even if the underlying physical principles were never expressed in scientific terms. Beneath the fields of Sakurai City in Japan's Nara Prefecture, archaeologists uncovered the remains of a settlement that appeared at a decisive moment in Japanese history. Makimuku occupied the southeastern Nara Basin near Mount Miwa, extending roughly 2 kilometers from east to west and about 1.5 kilometers from north to south. Although scattered remains had been reported earlier, the site's true scale became clear after rescue surveys in the 20th century exposed a canal-like feature approximately 5 meters wide, 1 meter deep and traceable for more than 200 meters. Later excavations revealed post holes, fences, wooden objects, ritual deposits, and unusually large buildings dating mainly from the late 2nd to the middle 4th century. Yet only a small fraction of the estimated settlement has been excavated, leaving most of its organization hidden beneath modern roads, houses, and farmland. What emerged from those trenches did not resemble an ordinary Yayoi farming village. Makimuku seems to have expanded with extraordinary speed around the beginning of the 3rd century, precisely when communities across the Japanese archipelago were beginning to form larger political alliances. Earlier settlements usually developed gradually around clusters of houses, storage pits, and rice fields, but Makimuku contained dispersed architectural zones, major watercourses, and spaces apparently intended for gatherings and ceremonies. Archaeologists have therefore described it not simply as a village, but as a political and ritual center whose population may have fluctuated as people arrived from distant regions. Its sudden appearance presents the first technical mystery. Such a place required surveying, land allocation, construction schedules, and control over labor, yet no administrative records, plans, or written calculations survive. The clearest evidence of centralized planning came from a group of buildings uncovered near the center of the site. Excavations beginning in 2009 identified several structures arranged along a shared east-west axis, including the foundations of an exceptionally large raised building, estimated to have covered about 238 square meters. The post holes indicate a timber-framed hall far larger than normal domestic architecture of the period. Its position within a carefully aligned compound, together with fences and neighboring buildings, suggests that the structures were conceived as a coordinated complex rather than added randomly over time. Some researchers have proposed that this was a palace or ceremonial residence associated with Queen Himiko. although no inscription identifies its occupant. Even without that royal interpretation, the engineering problem remains. A building of this scale required large, straight timbers, accurately spaced post holes, and a structural system capable of supporting an elevated floor and heavy roof. The builders possessed no iron machinery, powered cranes, or preserved architectural drawings. Timber could have been raised with ropes, temporary earthen ramps, and coordinated labour, but the site has preserved almost none of the temporary equipment involved. Because wood decays in the humid Japanese climate, archaeologists are left with negative impressions in the soil rather than beams, joints, or roof frames. The geometry of the foundations demonstrates that the builders could reproduce measured intervals and maintain alignment across multiple structures, while the practical methods that made this precision possible have almost entirely vanished. That lost knowledge becomes more difficult to explain when Makimuku's water system is considered. The large canal discovered during early investigations was not an isolated ditch, but part of a landscape containing natural streams, modified channels, and drainage features. Building on an alluvial fan created opportunities for access to water, but it also exposed the settlement to seasonal flooding, erosion, and unstable sediments. Channels therefore had to be positioned with sufficient gradients to carry water without rapidly cutting into their banks or leaving stagnant pools. No evidence proves that Makimuku possessed a fully integrated hydraulic grid, yet the scale of the excavated watercourse shows that substantial collective labour was invested in controlling movement through the landscape. Whether the canal primarily carried water, defined ceremonial boundaries, transported materials, or served several purposes remains disputed. The mystery deepens because Makimuku is connected to regions far beyond the Nara Basin. Pottery analysis has identified vessels or stylistic traditions associated with Tokai, Hokuriku, Sanin, Kawachi, Kibi, Omi, Kanto, Harima, the Western Seto Inland Sea, and Ki. Some published assemblages suggest that pottery with external regional characteristics formed an unusually high proportion of the material recovered from ritual areas. These objects are not merely evidence of trade. Pottery was normally heavy, fragile, and relatively inexpensive, meaning that transporting it over long distances was often less efficient than carrying rare metals or ornaments. Its presence may therefore indicate that people themselves were travelling to Makimuku and bringing familiar vessels with them. If that interpretation is correct, the settlement functioned through a logistical network extending across much of central and western Japan. Travellers had to cross mountains, rivers, and inland seas in an age without a standardized road system or written travel administration. Food, timber, and ceremonial supplies had to be gathered for assemblies whose size is unknown. Makimuku may thus preserve evidence for an early system of political coordination before the appearance of a fully documented state. Archaeology can map the origins of ceramics and compare regional manufacturing techniques, but it cannot yet reveal who organized these movements, how obligations were enforced, or whether communities participated voluntarily, through religious authority or under political pressure. Material recovered from ritual deposits shows that large gatherings were not purely administrative. An oval pit near the major building complex contained approximately 2,000 peach seeds, one of the largest concentrated deposits of its kind discovered in Japan. Excavators also recovered fish remains, including marine and freshwater species, together with more than 1,000 bones from animals such as deer, wild boar, and birds. Peaches were associated with purification and protection in later East Asian traditions, while the mixture of food remains suggests repeated consumption or offerings on a considerable scale. Yet the deposits cannot establish exactly what ceremonies occurred or whether they were performed for a ruler, a deity, or a coalition of regional leaders. Makimuku's greatest demonstration of organized engineering may lie beside the settlement, rather than within its buildings. The surrounding landscape contains some of Japan's earliest monumental burial mounds, culminating in Hashihaka Kofun, a keyhole-shaped tomb approximately 280 meters long. Constructed around the middle of the 3rd century, it represents a dramatic increase in the scale of funerary architecture and is widely associated with the emergence of Yamato political power. Creating it required the excavation, transport, and placement of enormous quantities of earth, along with the geometric control necessary to form a circular rear mound joined to a projecting rectangular section. Even when thousands of workers are assumed, the construction demanded coordinated surveying, standardized tasks, and a reliable food supply over an extended period. This uncertainty lies at the center of the debate over Yamatai, the kingdom described in the Chinese chronicle known as the Weiji. The text records that Queen Himiko ruled a federation of communities during the 3rd century and maintained diplomatic contact with the Chinese state of Wei. Makimuku fits the general chronology and possesses the scale, ritual character, and regional connections expected of a major political center. Hashihaka was also built near the period traditionally associated with Himiko's death. Nevertheless, no inscribed object naming Himiko or Yamatai has been found at the site, and the archaeological record cannot by itself prove that the Chinese name referred to this precise location. Castro de Sanchuy was identified in the early 1950s on a mountain ridge near San Martín de Peduledo in the municipality of Allende, western Asturias, northern Spain. Rising between approximately 740 and 780 meters above sea level, the fortified settlement occupies about 2.8 hectares and overlooks the valleys formed by several tributaries of the Narcia river system. Local resident José Lombardia Zardane first drew attention to the ruins, and systematic excavation began under archaeologist Francisco Jorda Cerda in 1962 and 1963, before continuing through several campaigns between 1979 and 1986. More than 20 structures were eventually exposed, while later investigations added topographic surveys, geophysical prospection, radiocarbon dating, charcoal analysis, and laboratory studies of pottery and metal objects. What emerged was not a simple cluster of Iron Age huts, but a settlement repeatedly rebuilt across centuries. Radiocarbon evidence, stratigraphy, and ceramic sequences indicate occupation beginning before the Roman conquest and continuing into the Roman period, although the precise duration and intensity of each phase remain debated. This long history is essential because Sanchuys preserves two architectural traditions within the same fortified space. In the lower sector, circular and curving indigenous buildings follow the contours of the hill, while the upper sector contains more rectilinear structures, shared walls, and paved routes associated with later occupation. The contrast reveals major social and technical change, yet it does not explain how the settlement was reorganized without destroying the defensive and structural logic established by earlier builders. The most visible technical achievement surrounds the inhabited area. Sanchuy was protected by a perimeter wall combined with ditches placed mainly where the terrain was easiest to approach. On the naturally steep northern and eastern slopes, the builders depended heavily on the mountain itself. Along the more vulnerable western and southwestern approaches, however, they created a far more complex barrier, including an advanced trench and as many as 6 lines of ditches and counter-ditches. This was not a symmetrical fortress designed from an abstract geometric plan. It was a defensive system adjusted section by section to changes in slope, bedrock, and exposure, meaning that its effectiveness depended upon an accurate practical reading of the landscape. That adaptation raises one of the central questions surrounding San Chuis. Archaeologists can map the surviving earthworks, but no measuring instruments, plans, or construction records reveal how the builders transferred a large defensive design onto irregular mountainous ground. The positioning of the ditches suggests that labour was concentrated where attackers could realistically advance, while unnecessary excavation was avoided on cliffs and steep slopes. Such decisions required more than physical strength. They demanded knowledge of visibility, access routes, soil behaviour, and the amount of manpower needed to remove and relocate large volumes of earth. The mystery is therefore not whether Iron Age communities were capable of planning, but how this planning was calculated, communicated, and maintained through successive generations without any surviving written technical system. The wall itself deepens the problem. Parts of the fortification have been described as modular, consisting of separate structural sections rather than one continuous undifferentiated mass. Modular construction could reduce the risk that the failure of one section would destabilize the entire circuit, while also allowing different work groups to build or repair sections independently. Yet the precise sequence of construction remains difficult to reconstruct, because later rebuilding, collapse, and restoration have altered parts of the evidence. Researchers can identify the final arrangement, but the temporary ramps, scaffolding, lifting devices, and work surfaces required to create it have disappeared. What remains is a finished defensive shell whose construction process is largely invisible. Inside the walls, the builders faced a different engineering challenge. The summit was not a level platform, so usable ground had to be created through retaining walls, stone foundations, and structures adapted to uneven elevations. Circular buildings were especially suited to these conditions because curved walls distribute roof loads without requiring long straight foundations across unstable ground. Their shape also reduces direct exposure to wind, an important advantage on an elevated ridge in the wet and frequently windy climate of western Asturias. However, these benefits alone do not explain how builders selected foundation points, controlled wall thickness, or prevented runoff from weakening structures during prolonged rainfall. No monumental Roman-style sewer has been identified across the settlement. Drainage appears instead to have depended on the combined use of natural gradients, open spaces, pathways, surface channels, and permeable stone construction. This apparently simple system could function only if floors, entrances, and circulation routes were positioned so that water moved away from occupied interiors rather than collecting against their walls. Because the settlement remained in use through repeated rebuilding, drainage cannot have been an accidental result of a single construction phase. Later inhabitants had to recognize the hydraulic logic of the existing ground and preserve it while adding new buildings. Yet archaeology has recovered no formal design that explains how this knowledge was transmitted. The contrast between circular structures and later rectangular buildings is often interpreted as evidence of Roman influence, but San Chuis does not show a complete replacement of indigenous construction by an imported urban plan. Instead, local and Roman practices overlapped. New walls sometimes followed earlier alignments, while traditional handmade pottery continued beside wheel-made and imported wares. Archaeometric research has examined pottery through technological operational sequences, studying clay preparation, forming, finishing, and firing rather than classifying vessels only by shape. These analyses show that technological change was selective. Communities adopted some external products and practices while retaining local manufacturing traditions, suggesting that Romanization was not a sudden technical revolution imposed on an empty landscape. Imported ceramics, glass, coins, and other Roman period materials also demonstrate that San Chuis was not an isolated mountain refuge. Its position connected it with routes crossing western Asturias, a region later transformed by Roman gold extraction. However, the scale and exact function of the settlement within those networks remain uncertain. It may have supervised local movement, housed an important community, or participated in the administration of nearby resources, but the archaeological record does not prove that it was a formal Roman military or mining centre. The presence of imported objects reveals contact and exchange, yet it cannot identify who controlled that exchange, or how goods were transported through terrain lacking the monumental roads and warehouses found in larger Roman cities. Environmental evidence adds another layer to the reconstruction. Charcoal recovered from archaeological deposits indicates the use of several woody species, including deciduous oak and vegetation associated with the surrounding mountain environment. Such studies help reconstruct fuel selection and local woodland exploitation, but they also reveal the practical demands of permanent settlement. Timber was needed for roofs, doors, tools, fires, and possibly defensive structures. Maintaining a community on the ridge therefore required organized access to woodland, water, agricultural land, and transport routes below. The excavated buildings show where people lived, but not the full logistical system that kept them supplied. Systematic excavations began in 1972 on the Castro de Santander hill near Canavruelas in Spain's Cuenca province. What emerged was not the Celtiberian stronghold described by the Roman historian Livy, but a later Roman city occupying a strategic promontory above the Guadiana River. Spread across approximately 20 hectares and enclosed by defensive walls, Erkavica had been laid out as a planned settlement with paved streets, houses, public buildings, and a monumental civic centre. Yet the deeper archaeologists excavated, the more difficult it became to explain how such an orderly city had been imposed upon this uneven and geologically complex hill. Livy first mentioned Erkavica during the campaign of Tiberius Sempronius Gracchus in 179 BC, describing it as a powerful Celtiberian city that surrendered after several days of resistance. The problem is that excavations at Castro de Santander have produced little material securely predating the second half of the 1st century BC. This has led some researchers to suspect that the original Celtiberian settlement stood elsewhere, possibly at Muela de Alcocha, a 37-hectare site roughly 6 kilometers upstream that is now partly affected by the Buendia Reservoir. Roman Erkavica may therefore have been an entirely new city that inherited the name and political territory of an older centre whose exact location remains disputed. That possibility makes the urban design even more remarkable. Roman Erkavica was founded ex novo, with streets arranged in an orthogonal pattern despite the fact that the hill was neither flat nor geometrically regular. Geological surveys describe the site as an elongated elevation composed of clays, sandstones, and limestone beds dipping by less than 10 degrees toward the east. These materials do not behave uniformly under structural loads. Clay expands and contracts with changing moisture. Sandstone erodes along weaker layers, and limestone can fracture or channel water through hidden joints. Before a single monumental building could rise, surveyors had to decide which zones could support masonry, where slopes required modification, and how rainwater would move beneath streets and foundations. The visible city suggests that this assessment was extraordinarily effective, but no construction plan survives to show how it was achieved. Roman surveyors possessed instruments such as the groma for establishing right angles, the dioptra for measuring directions, and the chorobates for checking gradients. These devices explain the principles of Roman surveying, yet they do not reveal the exact working sequence used at Erkavica. On a hill where the natural surface constantly rises, falls, and changes composition, a regular street grid could not simply be marked out and built. Elevations had to be transferred across obstructed ground, slopes had to be cut or filled, and the alignment of one district had to remain consistent with another, even when the surveyors could not see the entire city from a single position. This challenge becomes clearest around the Forum, where architecture was used to manufacture level space rather than merely occupy it. The civic centre included a rectangular paved square, porticos, a judicial basilica, shops, and a monumental eastern extension supported by a two-level cryptoporticus. A cryptoporticus is partly an underground structure, but at Erkavica it also functioned as an enormous artificial platform. Instead of following the hillside, the builders created a horizontal surface above it, transferring the weight of paving, columns, walls, and crowds into lower masonry that had to resist both vertical loading and lateral pressure from the surrounding ground. The engineering logic can be reconstructed in general terms, but many practical details remain invisible. The builders must have controlled the thickness of foundations, selected stones according to their position, and allowed water to escape from behind retaining structures. Otherwise, saturated earth would have increased pressure against the walls and gradually forced them outward. Yet the temporary works needed for such construction have vanished. No complete lifting system, scaffold network, or transport ramp survives, and archaeology preserves the finished platform far more clearly than the sequence that produced it. What remains is the result of calculations that were never written down at the site. The same precision appears in the residential districts. Houses were arranged within blocks defined by cobbled streets, while major routes followed the principal north-south and east-west axes. The so-called House of the Doctor was organised around an atrium with an impluvium, a sunken basin designed to receive rainwater from the roof. This familiar Roman feature was more than decoration. It formed part of a controlled hydraulic circuit in which roof geometry, gutter position, floor slope, and underground storage all had to work together. A small error in gradient could send water into adjoining rooms, undermine wall foundations, or leave stagnant pools within the house. At Erkavica, water management was not optional. The city stood on elevated ground selected for defense and visibility, not because it offered an abundant river beside every neighborhood. The Guadiella flowed below the hill, but raising large quantities of water to the settlement would have demanded sustained labor or mechanical lifting. Rainfall could be collected from roofs, courtyards, and paved surfaces, yet seasonal collection required storage capacity and careful protection against contamination. Cisterns, basins, drains, and domestic impluvia therefore reveal an integrated response, although the complete supply network has not been recovered. This uncertainty is important because the surviving hydraulic features show that the inhabitants understood water as an urban system rather than a collection of isolated structures. Streets had to shed stormwater without eroding their surfaces. Houses needed drainage that would not discharge into neighbouring foundations. Public buildings required clean water while waste moved away through separate paths. Beneath this planning lay another difficulty. The hill's alternating beds of permeable and less permeable material could redirect water underground. Engineers who ignored those conditions risked creating hidden zones of saturation capable of weakening terraces and walls. The Roman solution often involved mortars made from lime, sand, and crushed ceramic material. In water-related structures, this mixture could produce opus signinum, a dense lining commonly used in cisterns, baths, channels, and pools. Crushed brick was not simply filler. Its silica and alumina-rich particles could react with lime in the presence of water, forming cementitious compounds that reduced permeability and increased long-term durability. Modern materials science describes this as a pozzolanic reaction, but the ancient builders reached the result without chemical formulas, standardized industrial kilns, or modern instruments for measuring grain size and moisture. Even so, describing the reaction does not recover the lost craft. The performance of such mortar depended on the quality of the lime, the firing temperature of the ceramic fragments, the ratio between aggregate and binder, the amount of water added and the length of curing. Craftsmen also had to prepare the underlying surface and apply the lining before the mixture lost workability. Laboratory analysis can identify mineral phases in surviving samples, yet it cannot fully reconstruct the decisions made during construction or explain how local workshops adapted their recipes to Akavaca's climate and raw materials. Stone transport presents a related problem. Monumental public buildings required large quantities of dressed limestone and other construction material to be moved onto the hill. The final distance from a quarry may have been modest, but the last stage of the journey was the most difficult because every block had to be hauled upward. Roman builders could use sledges, rollers, wooden cranes, capstans, and coordinated teams of labourers or animals. However, those are possibilities based on wider Roman practice, not a complete reconstruction supported by surviving equipment at Akavaca. The absence of machinery does not make the construction supernatural. It reveals how little temporary infrastructure normally survives. Wooden lifting frames decayed, ropes disappeared, earthen ramps were dismantled, and metal fittings were recycled. Archaeologists are therefore left with foundations and finished masonry from which they must work backward. Tool marks can suggest how stones were shaped, while wear patterns may indicate where loads were dragged, but neither provides the full logistical chain connecting quarry, workshop, transport route, and final placement. Geophysical research has added another layer to this investigation. Electrical resistivity and electromagnetic surveys have been used to detect buried variations beneath the site, allowing researchers to identify possible walls, voids, and architectural features without excavating every area. Such methods work because stone foundations, compacted floors, and moisture-filled deposits conduct electrical energy differently. The resulting maps demonstrate that much of Akavaca remains hidden, meaning that interpretations of its streets, hydraulic network, and structural organization are still based on an incomplete sample of the city. In 1898, the historian Bernardo Acevedo y Huelves recorded ancient ruins above the Pendia River near the village of the same name in Boal, Western Asturias, Spain. More detailed observations followed in 1929, but the settlement remained largely buried until Antonio Garcia y Bellido and Juan Uria Riu began excavating it in 1941, while working simultaneously at the larger hill fort of Coana. What emerged was an unusually compact, fortified community, divided into a residential quarter and an elevated acropolis, separated by a substantial internal wall. Yet, its most remarkable feature was not its houses or commanding position. Within this small enclosure stood two stone buildings now interpreted as Iron Age steam baths, a concentration of ceremonial architecture that remains difficult to explain. Pendia developed within the Castro culture that occupied northwestern Iberia during the Iron Age and continued to evolve after Roman expansion into Asturias. Hill forts of this tradition were normally protected by walls, ditches, and naturally steep terrain, but Pendia appears exceptionally defensive for the limited space enclosed. Its builder selected a narrow rocky ridge whose slopes already restricted access, then reinforced it with artificial barriers and masonry walls. Such work consumed stone, timber, and labour that could otherwise have supported agriculture or housing. Defensive architecture may also have advertised communal power, yet the surviving settlement contains only a modest number of buildings, creating a persistent imbalance between the population the hill could accommodate and the effort invested in protecting it. This imbalance becomes even stranger at the internal wall separating the settlement from the Acropolis. A purely military explanation would suggest that the elevated sector protected leaders, stored valuables, or provided a final refuge during attack. However, excavation has not produced a palace, archive, or unmistakable treasury capable of confirming any of those functions. The Acropolis instead preserves an elongated structure, unlike the mostly rounded domestic buildings below. Its purpose remains uncertain, and because only part of the site has been fully investigated, archaeologists cannot determine whether this upper enclosure represented political authority, restricted ritual space, or a defensive position serving several functions at once. Building upon such a ridge required more than raising a perimeter wall. The natural surface was too irregular to receive closely packed houses without modification, so the inhabitants created usable platforms by cutting into higher ground and retaining deposits along the slopes. Walls, therefore, performed several tasks simultaneously. They enclosed rooms, stabilized terraces, and redirected pressure through the settlement. The masonry was assembled largely from locally available stone without modern cement, relying upon careful placement, friction, and the mass of the wall itself. Irregular stones were not simply piled together. Larger pieces strengthened the faces, smaller material filled internal voids, and the thickness of the construction distributed loads across a wider base. The survival of these structures for roughly 2 millennia is significant because Western Asturias is a wet Atlantic environment where runoff penetrates joints, removes fine sediment, and gradually destabilizes poorly drained terraces. Pendia's builders had no written geotechnical calculations, yet they understood that water and gravity were inseparable problems. Floors, passages, and exterior surfaces had to shed rain before it accumulated behind retaining walls. Even minor failures could have increased hydrostatic pressure, pushed masonry outward, and caused entire platforms to collapse. The remaining architecture suggests a construction tradition based upon long observation of local stone, soil, and seasonal rainfall, although the exact drainage network cannot be reconstructed because later erosion, excavation, and restoration altered parts of the original surfaces. The houses reveal the same adaptation to restricted terrain. Curved and rectangular plans were fitted closely together, rather than arranged on a spacious geometric grid. Their walls follow the shape of the ridge, leaving narrow passages that controlled movement through the interior. This was not random growth in the modern sense, because each new building depended upon the stability, access, and drainage of those already present. A house placed incorrectly could block circulation or direct roof water toward a neighbouring foundation. Pendia consequently preserves evidence of cumulative planning, but no measuring instruments, marked construction templates, or written instructions have survived to show how dimensions were transferred from one structure to another. Transporting the required material created another problem. Although stone could be obtained locally, every block still had to be detached, shaped when necessary, and moved across steep ground. The final walls represent many tons of material, yet no permanent ramp system or lifting installation has been identified. Timber sledges, ropes, levers, and coordinated human labor provide plausible solutions, but they remain reconstructions based on technologies known elsewhere rather than equipment recovered at Pendia. The finished architecture survives while the temporary structures that made construction possible have disappeared, leaving archaeologists able to study the result but not the full sequence of operations behind it. At the center of this engineering puzzle are the two buildings traditionally called castrosaunas. Such structures are known from a limited number of fortified settlements in Asturias, Galicia, and northern Portugal, where they have generated debate since the 19th century. Early investigators variously describe them as ovens, kilns, or cremation installations. Comparative architectural research now supports their interpretation as bathing or steam-producing buildings, yet their social purpose remains uncertain. They may have served purification, healing, initiation, communal identity, or several related activities, and the presence of two at Pendia is especially unusual for a settlement of such restricted size. The older structure is generally regarded as pre-Roman. Its surviving plan included a semicircular furnace, a rectangular chamber, and a vestibule that is now poorly preserved. Producing steam required controlled heating inside a building whose roof and upper walls have vanished. Stone, earth, timber, and possibly clay components had to withstand repeated cycles of heat, moisture, and cooling without cracking dangerously or losing too much energy through the envelope. The position of the furnace and chamber suggests that heat was deliberately confined, but the precise movement of hot air, the quantity of fuel consumed, and the method used to introduce water cannot be measured directly from the ruins. The second sauna appears to belong to a later architectural phase associated with Roman period occupation. This chronological difference is crucial because it suggests that the practice was not a brief experiment. The community either replaced an older installation, constructed an alternative form, or maintained two buildings intended for different groups and ceremonies. None of these possibilities can yet be demonstrated. If one building simply succeeded the other, archaeologists must explain why both remained recognizable within such limited space. If they operated at the same time, Pendia possessed a ritual capacity disproportionate to its residential population. Their operation also depended upon fuel management. Repeated heating would have required a dependable supply of wood gathered from the surrounding landscape, dried and stored before use. Poorly seasoned timber produces less efficient heat and more smoke, while uncontrolled combustion could damage the chamber or make it impossible to occupy. Ventilation therefore had to remove combustion gases without releasing all the heat needed to generate steam. Because the superstructures are lost, researchers cannot determine the original height of the rooms, the form of their roofs, or whether adjustable openings regulated airflow. Any modern reconstruction must therefore make assumptions precisely where the most important thermal evidence has disappeared. Water presented an equally complex challenge. A steam bath required more than access to a vessel carried by hand. The builders had to prevent hot water and condensation from saturating floors, eroding wall foundations, or spreading into adjacent structures. In a compact hill fort where buildings stood close together, repeated discharge in the wrong place could gradually undermine the settlement itself. The survival of the bathing complexes indicates that moisture was managed deliberately, but the archaeological remains do not preserve a complete hydraulic circuit comparable to the pipe systems of later Roman baths. Pendia's saunas were not miniature Roman thermae. They belonged to a regional technological tradition whose practical knowledge was transmitted without surviving manuals. Castro de la Loma stands in the mountains of northern Palencia, Spain, rising above the surrounding valleys as one of the largest known Iron Age strongholds of the ancient Cantabria. Long before Rome completed its conquest of Hispania, this fortified settlement occupied more than 10 hectares on a naturally defended plateau. Yet its greatest mystery is not its size, but the engineering knowledge that allowed its builders to create a fortress capable of resisting both invading armies and more than 2,000 years of erosion. The site remained largely unnoticed by modern archaeology until systematic surveys and excavations during the late 20th and early 21st centuries revealed extensive defensive structures spread across the hilltop. Archaeologists documented massive stone walls, deep ditches, habitation areas, and, even more remarkably, the remains of Roman siege works surrounding the settlement. The combination of indigenous fortifications and Roman military camps provided rare physical evidence of the Cantabrian Wars, fought between 29 and 19 BCE, allowing researchers to reconstruct one of the final campaigns that brought northern Iberia under Roman control. Yet excavation quickly transformed a historical site into an engineering puzzle. Castro de la Loma occupies terrain that appears almost designed to discourage construction. Steep slopes fall away from the plateau on several sides, while exposed limestone and unstable soil create conditions that remain challenging even for modern builders. Despite these obstacles, the ancient inhabitants created an organized settlement enclosed by walls several meters thick, carefully adapting every section to the contours of the landscape instead of forcing the landscape to fit a geometric plan. This flexible design required detailed knowledge of gradients, drainage, and structural stability without the benefit of written engineering manuals or surviving measuring instruments. The greatest unresolved question concerns the enormous defensive walls themselves. Many surviving sections still stand upon foundations that have resisted gravity, seasonal rainfall, freezing winters, and continuous erosion for more than 2 millennia. Northern Spain experiences repeated cycles of water infiltration, frost expansion, and soil movement, processes that gradually destroy poorly designed masonry. Modern geotechnical studies demonstrate that hydrostatic pressure accumulating behind retaining walls is one of the principal causes of structural collapse. Yet, Castro de la Loma shows surprisingly little evidence of catastrophic foundation failure across large portions of its defences. This suggests that its builders understood principles that modern engineers would recognise as drainage control and load distribution, even if they described them very differently. One explanation proposed by archaeologists is that the walls were never intended simply as vertical barriers. Instead, they functioned as integrated retaining systems anchored directly into the bedrock, while following the natural shape of the hill. Rather than opposing gravity, the walls appear to cooperate with it. Large limestone blocks formed stable outer faces, while carefully selected smaller stones filled internal spaces, allowing limited movement without triggering complete collapse. Because dry stone construction contains countless microscopic gaps, infiltrating water can escape instead of building destructive pressure behind the structure. Similar principles are recognized today in dry retaining walls used in difficult terrain, but the precise construction sequence employed at Castro de la Loma remains unknown because the temporary wooden frameworks, ramps, and lifting devices disappeared centuries ago. Equally remarkable is the selection of construction materials. Geological surveys indicate that the builders relied primarily on locally available limestone, reducing transport distances while exploiting stone already adapted to the regional climate. Limestone expands and contracts less dramatically than many weaker sedimentary rocks under seasonal temperature changes, contributing to long-term stability when properly assembled. Even so, transporting thousands of heavy blocks uphill using Iron Age technology presents another unresolved engineering problem. Experimental archaeology demonstrates that timber sledges, wooden rollers, ropes, and coordinated labour can move stones weighing several tons, but no direct archaeological evidence for these transport systems has survived at Castro de la Loma itself. The finished walls remain visible, while every temporary device that made their construction possible has vanished. As researchers examine the surrounding defences, another sophisticated feature became apparent. The walls rarely follow straight lines for long distances. Instead, they bend, angle, and adjust repeatedly to the terrain, creating overlapping fields of observation that reduced blind approaches for attackers. Military historians recognize that angled defensive layouts force advancing enemies into positions where defenders can observe multiple directions simultaneously. Whether the Canterbury independently developed these concepts or gradually refined them through generations of warfare remains uncertain. Unlike Roman military manuals, no indigenous written records explain the reasoning behind these designs, leaving the surviving architecture as the only testimony to their strategic thinking. The enormous defensive ditch surrounding parts of the settlement raises equally difficult questions. Excavation revealed trenches several meters deep and exceptionally wide in places, representing the removal of tens of thousands of cubic meters of earth and rock. Completing such an undertaking using Iron Age iron picks, wooden shovels, and manual labour would have required extraordinary organisation. Archaeologists suspect that much of the excavated material was reused to strengthen embankments and reinforce defensive lines. Yet no complete reconstruction of the construction sequence has been achieved. The absence of obvious spoil heaps indicates that excavation and construction were probably planned as a single integrated engineering operation rather than two independent activities. Inside the enclosure, the settlement displays evidence of careful spatial organization rather than random expansion. Houses, circulation routes, and defensive zones appear intentionally distributed across the plateau, despite its irregular topography. Modern LiDAR surveys have revealed subtle terrain modifications almost invisible from ground level, suggesting that builders reshaped portions of the landscape before construction began. Such planning required reliable methods of surveying distances and elevations, although no measuring rods, templates, or written plans have been recovered. The settlement therefore demonstrates organized civil engineering without preserving the tools or documents normally associated with large construction projects. Perhaps the strongest indication of Castro de la Loma's defensive strength comes not from the settlement itself, but from the army sent to destroy it. Archaeological investigations have identified Roman siege camps surrounding the hill, complete with earthworks and military layouts, characteristic of Augustus's campaigns during the Cantabrian Wars. Rome possessed one of the most experienced professional armies of the ancient world, yet the existence of extensive siege infrastructure suggests that direct assault alone was considered too costly. Instead, the Romans invested time and manpower in systematic encirclement before ultimately capturing the fortress. Burn layers, collapsed masonry, Roman weapons and projectile points discovered during excavation all indicate that the settlement met a violent end rather than a gradual abandonment.